Okay. Hey, welcome everybody. Welcome to the sixth installment of semi-virtual RQI. Now broadcasting from Macquarie. We'll give technical thanks to technical people at the end. So now, without further ado, let me introduce the first morning speaker, our own Macquarie's Pravin Dahal. Pravin, it's all yours.
Thank you for this opportunity. Especially, it's a privilege to have an opportunity to present the talk at first. So today I am going to talk on how to extract Hawking temperature of dynamical black holes via conformal transformations. Basically, so this was the continuation of our work on extracting the Hawking temperature of dynamical black holes, and on our previous work we used Rindler transformations, and in that work, so we analyzed, we took the near horizon region of black holes, and in the near horizon region we did Unruh Hawking analogy, or especially took the reference of uniformly accelerating observer, and based on that, so we extracted the temperature. So basically, so the motivation and the next logical step of this talk is as follows. So we are first talking about the background. So why we talk about dynamical black hole, and on dynamical black hole, so we take a specific example, specific dynamical metric. So why we take that metric? So basically, we study, or we try to find semi-classical self-consistent solutions to find the near horizon region. So to find the solutions of ultra compact objects. So what are the solutions, or what is the generic solutions on semi-classical gravity? So that contains horizon on ultra compact objects. So we first discuss about that, and then so after like obtaining solutions, some of the solutions on semi-classical gravity, so we see like, or we try to find if there are some dynamical solutions which are non-trivial one, and which are relevant, or like which are popular in literatures. So indeed there are, and then on some particular solution, on a particular solutions which is of specific interest, we try to investigate Hawking radiations and the thermodynamics. So basically we first talk about physical black hole solutions in semi-classical gravity, and indeed the Vedl metric, or Vedl space-time, which is the space-time of evaporating black hole, falls onto that category. So we take the particular model of linear Vedl space-time to study Hawking temperature and the thermodynamics. So let's start first with physical black holes. Our first, like, we work in metric theory of gravity. So we here like specific our discussions to spherically symmetric spacetimes, and on that spherically symmetric spacetime, so we can write metric in this way. So this is the most generic metric in spherically symmetric spacetimes, and this is like in what we call Schwarzschild coordinates. If you look carefully at this metric, so this has two arbitrary functions, and like, so yeah, basically two arbitrary functions constraining these two independent functions are sufficient to constrain the metric in spherically symmetric settings, and these two functions completely characterize the space-time geometry. So, and another thing to notice here is like we are writing in this like familiar form, which we basically see in any spherical coordinates, in Menicucci spacetime, and this like familiar forms of angular variable has the metric like radial metric as metric r, and we call that coordinate as areal radius. And that areal radius, writing metric in this form, allows us to characterize so this function in coordinate independent way. And if we define this function in this way, so we call this m, which arises from coordinate independent way, as Misner's short mass. And So of course, like this metric is coordinate dependent thing, but like a general spherically symmetric space-time, in general space-time we can construct invariant quantities, and we here focus on invariant quantities which are derived from Riemann curvature tensor, which is basically constructed from metric and its derivative of the second derivative, and so we can construct a lot of like invariant quantities, and depending on the generality of our space-times, like spherically symmetric space-times or axially symmetric space-times, so some number of these quantities are sufficient to constrain sufficient to sufficient to constrain the space-time geometry or characterize the space-time geometry. So we talk about physical black holes and we talk about horizon. So let's us first introduce like what we mean by horizon. So basically one of the most popular notion of horizon is event horizon. And when we talk about horizon in static black hole settings, so that horizon means event horizon. So that is the boundary where like from which the outside observer is not affected by the phenomena occurring inside in black hole settings, but like there are event horizon in cosmological settings also, which we don't talk here, although like our like specific semi-classical settings applies to cosmological settings also. So basically by this definition, so event horizon is a global teleological entity, which means that like one needs to understand the entire history of the universe to find its location, and for it, so in that sense event horizon is unobservable, because like any mortal observers has no like that long amount of time to track its locations, and thus like for practical studies, so we focus on another characteristics of black hole. Basically, so by definition of black hole, so what we mean is dragging back of light, and that dragging back of light so can be expressed mathematically using the notion of closed trapped surface, like from which like light cannot escape now or at present, so we don't know about future. So physical black hole is an object containing that closed trapped region from which like light is dragged back or pulled back, and the outermost like boundary of that trapped region is called apparent horizon. For the metric we have shown before, for general spherically symmetric metric, the apparent horizon is located at r equals twice m, which is important for later calculations. Another thing is we define another new notation T mu nu, which we don't say as energy momentum tensor here. We just denote this. We just write it to denote Einstein tensor, which is the quantity on right hand side. And in spherical symmetry, so there are like a lot of curvature invariants, and there are works which has shown that like 16 are curvature invariants. So if you consider perfect fluids is sufficient to completely characterize any like general metric. So deriving from where like if we consider energy momentum tensor as perfect fluid, but spherical symmetry is very simple case, and 3 of the curvature invariants are sufficient to constrain the geometry, spherical symmetric geometry. And among 3 of the curvature invariants, 2 of them are here. So one is basically contraction of this thing, Einstein tensor with g mu nu, and another is its square. We can write them as individual components in these different ways. And if we notice here, the denominator has quantities which goes to 0 at horizon, so based on the definition of apparent horizon. And if this quantity goes to 0, so for curvature invariants to be finite at the horizon, so we should have some constraint on the quantity in the numerator. Basically, they must be equal in the order of calculations we are considering for these curvature invariants to be finite. So first thing is we demand finiteness of these curvature invariants. And another thing is we demand that this equation holds true. Basically in semi-classical gravity, so this equation is conservation equation, but this time we are not considering this T mu nu as energy momentum tensor. So this is just Einstein tensor, and these equations in semi-classical settings going to be true means that Bianchi identity is satisfied here, and this thing is completely generic to all metric theories of gravity. So if we substitute the first equation of the metric I have shown onto this equation, so we have only two non-trivial equations in spherical symmetry, and so of course we have only two non-trivial equations, but we make some more assumptions as we are focusing on near horizon solutions. So we assume that perturbative solutions exist near horizon, and we take the following answers to constrain this one of the variable in terms of this function. So near horizon expansion, we assume that this form of near horizon expansion exists. So now, like substituting these answers into these two non-trivial equations we have got from that Bianchi identity. So we obtain only one independent equations, and this independent equations has this form, which is like not which cannot be solved exactly, but it's not necessary to solve exactly, in the sense that we are focusing on near horizon solutions and we are doing perturbative expansions near horizon. So even like getting exact result doesn't make sense. So if we have only one independent equations, we have started with answers with two independent functions. So we don't have enough number of equations to determine exact value of beta. So if we look at beta here, so this is the power of near horizon expansions. But what we know is like we are focusing on the solutions with horizon. So like as we approach horizon, as r goes to twice m, which is like approaching horizon, so the quantity must go to 0. So for that answer to go to 0, beta must be greater than 0. So that's the only constraint we can say about beta. And so if we impose static limit on these differential equations, we have these specific solutions. So static black hole solution in any metric theory of gravity should preserve short side form. So should be written in this form, otherwise it would be inconsistent with the Bianchi identity and the assumption of regularity of curvature invariance. Now just we are demanding, so not constraining only to the static solutions, but demanding or focusing on the dynamical one. We have this specific form on the first function based on the second function based on the answers on the first function.
Pravin, but that's true. That's true only near the horizon.
Yeah, that's true only near the horizon.
It's not a general relation.
No. Because like we are starting from finiteness of curvature invariance, and we are like focusing already on the near horizon on that assumption, and on second assumption which we are taking specific perturbative expansion on these answers are r minus twice m. So this is only valid near horizon, and from this solution we can see that like so RG, so because of this plus minus sign, so we have one is accreting and another is evaporating solutions, growing and shrinking solutions. So the near horizon form of the metric in general settings is this form. So we have now constrained as much as we can based on that identity. And so on literature, so recently work on quantum gravity and like finding so perturbations based on quantum gravity. I have seen solutions, dynamical solutions, which does not satisfy this form, and I think like based on this assumption and working here, those solutions are not even compatible in the semi-classical gravity. So so does that solutions or is that solution compatible with any of the solutions known or popular solutions in the literature? Surely they are. In the sense that like we have Vedl metric, which represents dynamical black hole solutions based on the collapse of null shell or like evaporation of null fluids. So that falls into this category. And if we write Vedl metric, especially in advanced coordinates, so it takes this form. So this is linear Vedl metric. And we can do, so in linear case, in linear evaporation case, we can do exact coordinate transformation. So we have coordinate transformation relationship to write this metric into the form I have shown before, or like explicitly this form, so it's compatible. And moreover, like in the limit of small evaporation, so by using Einstein equations, so not possible in this framework, but by using Einstein equation, we have shown that Vedl space-time solves a very good near horizon approximations under some assumption. So comments on that. So our calculations does not particularly rely on specific metric theories of on any specific theory of gravity. So it's valid in all metric theory of gravity. So I have seen specific interesting example. For example, in rational gravity, people consider that like the divergence of EMT is not valid, and it starts from that assumption. What if like divergence of energy momentum tensor is not valid? However, like our theory or like our framework is applicable in that case also.
Okay. So sorry, divergence, you mean divergence is not zero?
Yeah, divergence is not
Bianchi
zero. Yeah, oh no, not Bianchi. Conservation of energy momentum tensor is not valid. But even like that is the metric theory of gravity. So Bianchi should be valid. And what I have seen from their solution is like it's hard to find dynamical black hole solutions in other metric theories of gravity. But like on their static black hole solutions also, they have taken the specific form of the metric which is compatible with the metric like I have shown before for static black hole solutions. So far so good here. Now like to analyze the evaporation thermodynamic property or like Hawking particle production in this semi-classical framework in these settings. So we take a specific example of linear Vedl. So because it is the simplest non-trivial solutions following from semi-classical gravity, and this linear Vedl space-time, so it's like a very interesting property that it is conformal to some static space-time. So if we have some static space-time, and if we multiply that static space-time by some conformal factor, then we have linear Vedl space-time. And if we have some static space-time, we can calculate event horizon of that static space-time. Although event horizon is a global concept, so not a local concept, not even quasi-local concept, but we can calculate event horizon in static space-time. And this conformal transformation has nice property that it preserves event horizon. So this event horizon is also the event horizon of linear Vedl metric. This notion of event horizon is imported in calculation of Hawking radiations. And another thing we need or we can generalize in these dynamical settings based on conformal transformations is the notion of Killing vector. So what are Killing vectors? So Killing vectors are infinitesimal generator of isometries, that is vectors like which preserves metric. For example, in static metric, so static metric is independent of time coordinates. So if we do any time translations, the metric doesn't change. So time translation is the Killing vector of static metric. So this can be generalized. This example can be generalized. So one can introduce the notion of conformal Killing vector in dynamical space-times based on the Killing vector in static space-times. So that conformal Killing vector is basically the Killing vector of corresponding conformal static space-time. For example, on linear Vedl metric, this particular example which we are referring to again and again has this form of conformal Killing vector. this is written in advanced coordinate and this is in static coordinate. And in static coordinates, it's clear that this is just some time translation vector. So from this conformal killing vector, we can define another notion of horizon, which is conformal killing horizon. And in static space-time, this conformal killing horizon basically coincides with event horizon. So, and event horizon is does not change on conformal transformation. So this horizon just give event horizon in this our dynamical case also, our dynamical settings. When we talk about particle productions, we start with generally Penrose process and superradiance and the possibility of particle production in core space-time, and then we go to spherical symmetric case and see how particle production happen. But like this Penrose process, if we talk about dynamical spherically symmetric settings, we can generalize to, or we can construct analogous process in spherically symmetric space-time also. So to explain Penrose process in spherically symmetric space-time, we need the notion of Kodama vector. So what is Kodama vector? So in spherically symmetric space-time, there exists an observer, like spherically symmetric observer, which respects the symmetry of the space-time. And based on that observer, one can define a geometric quantity known as Kodama vector. So this vector is time-like outside the apparent horizon and space-like inside it. And up to normalization factor, Kodama vector coincides with killing vector whenever both exist. So this is just the generalization of killing vector to dynamical spherically symmetric cases. And if we have Kodama vector, then we know like Kodama vector is time-like outside horizon and null inside and space-like inside horizon. So in spherically symmetric dynamical space-time, there exists a region between the event and apparent horizon, which we call quantum ergosphere, and in that region it is possible. In that region, since like it is between apparent and event horizon, particle can escape from that region. However, particle could also have negative energy in that region because Kodama vector could have is space-like in that region, and because of that, like some physical form momenta, some particle can have negative energy in that region, and thus we can import the phenomena of Penrose process in this dynamical space-time, Penrose process of axially symmetric case into the spherically symmetric case in dynamical black holes. 5 minutes, okay, thanks. And after that, so this possibility of like superradiance like process in spherically symmetric case. So we turn into a particle production. So let me skip this and just mention that like if we consider field equations in Minkowski spacetime, we can expand field equations into positive and negative frequency modes, and these modes are specifically well defined in Minkowski spacetime in flat spacetime settings because of the existence of global time-like killing vector. However, in chord spacetime, so this decomposition has no meaning because like so there doesn't exist this unique decompositions. We can decompose in like different ways, and but however like we still like mathematically we still do these decompositions, and the functions, the modes fk and fk star, it's possible that they could form a complete basis of solutions in chord spacetime. So let's take the field equations like in flat spacetime in this chord spacetime settings, and as we are considering conformal case, conformal case. So if we transform metric in this way, and if we transform the field in this way, these field equations remain unchanged. So to find the explicit solution of the field equations in linear Vaidya background, we first find the solutions in static background, and thus like we have reduced the problem of dynamical problem into static problem, and we will solve in static background, and we will by these conformal transformations transform into dynamical case. apparently in that static background, field equations was exactly solvable and can be reduced to Hune differential equations. So this is the incoming mode, which is different from Schwarzschild case, but outgoing mode is not so different, and one can express outgoing mode in terms of incoming modes. So outgoing functions in terms of incoming functions, because like they form complete basis, and from that one can extract, like by Fourier transformations, one can extract these alpha and beta coefficients, which are Bogolubov coefficients. So I'm not going to talk about this, but what I am going to say is we can exactly solve Bogolubov coefficients, and we can write the Bogolubov coefficients in this form. So two Bogolubov coefficients by solutions or by calculations. And based on that, so if we have relations between two of the Bogolubov coefficients in this way, we can extract Hawking temperature for Vedl geometry, and that temperature we can see here is constant, which is very surprising thing. But like it's not a surprise that various people has proposed that like the temperature in Vedl background should be constant, and they have related that to geometric surface gravity and calculated geometric surface gravity explicitly, and they have found exactly this quantity. So just to say in context of figure what happening, so this is the section of the static diagram, and this whole section contains is the Vedl diagram. So after evaporation, so what we are seeing as constant temperature is observed by the observer here, and if we like extrapolate that like to the observer associated with scribe plus, then that temperature like won't necessarily be constant. So we need to renormalize that constant temperature, rescale and renormalize that constant temperature to obtain the temperature observed by observer at infinity on Vedl background, and that will be 1/4 MB. And yeah, so this was just the literatures which were talking about temperatures on dynamical backgrounds, on conformal, on dynamical background which are conformal to static spacetime, but without exact derivations, some speculations. These were the papers talking about that, and our like result matches with this result, or like their speculations or their thoughts, their arguments. And this is my conclusion. So basically, thank you. So I'm extremely sorry that last half was a bit rough, but still.
A couple of interesting things. So, I'll have to poke your brains about any specific questions. Okay, so then let's thank Pravin, and Ioannis will have to start setting up.
Yeah.
In the meantime, speakers, please try to stay close to the screen and between the pink lines.
I just pressed click share. So. Okay. So are we good to start?
So our next talk is again by our own Ioannis Soranidis, and also about black hole, a little bit of information, and all the rest of the interesting stuff.
Good morning, everyone. Thanks, Danny, for the introduction. So today I'm going to talk about implications of singularity regularization in black hole thermodynamics. And this talk is going to be based on the following three papers. The first one is in collaboration with Sebastian Merck from Okinawa Institute of Science and Technology in Japan. Second one with Fil Simovic from Macquarie University. And the last one is by myself. So quantum gravity has been a long-standing quest, although with limited success thus far, and we expect that if such theory exists in nature, it will describe it at a reasonable accuracy, and singularities will not occur, and paradoxes such as the infamous black hole information paradox should not arise. But in the absence of such a comprehensive theory of quantum gravity, it would be useful to study effectively its properties and see if we can get some insight on how to proceed. And to do that, we need to find appropriate laboratories to perform these studies. And these should be regions of space-time that admit strong gravitational fields. Without any reasonable doubt, we know that such objects exist in our nature and are ultra-compact objects, and they can neither have the property of a horizon or not. If they don't, they are horizonless configurations. If they have the property of a horizon and under the quantum gravity theory assumption, we can have singularity, so they are regular black holes. A full classification of objects with horizon can be found in the review paper here by Mann, Mark, and Terno. And today I'm going to focus on the regular black hole case. So one reasonable question is, how do we source these geometries in the context that we have the tools to study them? So one of the ways is to have nonlinear electrodynamic theories and couple them to general relativity. So AEDT theories have been successful in the past eliminating singularities associated with the electric charge, such as Born-Infeld theory. Apparently they can do the same for gravitational singularities, but only at the cost of introducing a magnetic charge, which has not been observed in nature thus far. We expect, as the Born-Infeld theory was replaced by quantum electrodynamics, a fundamental theory like quantum gravity will replace this effective way of generating these geometries. Another way to generate these geometries is by using Gauss-Bonnet corrections to the Einstein-Hilbert action. And in order to have non-trivial contributions from this correction, we need to add a scalar field in 4 dimensions. And last but not least, look, quantum gravity can also generate regular geometries. But today I'm going to focus on the first case where we have general relativity coupled to anything, and I'm going to restrict even further in the case that we don't have any electric charge and we have spherically symmetric cases. So under these assumptions, we have a 4 potential that has this particular form and depends only on the magnetic charge Qm. And the action of such a theory is given by this form, where R is basically the scalar of space-time, lambda is the cosmological constant if present, and L of F is the NED Lagrangian density, where F is the field strength and it's calculated by the contraction of the electromagnetic field tensor. And in this case we're studying, we can calculate that it depends on the magnetic charge and the radial distance R. There are NED theories that depends on the dual scalar as well, but I will not talk about them today since NED Lagrangians that depend only on the field strength are sufficient to generate geometries that I'm going to study today. So, as I said, we will study spherical symmetric cases, so we will have a line element of this form, where f of r will be the metric function. And in order to demonstrate some of the thermodynamic properties in the second part of my talk, I'm going to use 3 specific regular black hole models that I'm going to introduce now. So the first model is the Hayward model. As we can see, the metric function depends on 2 parameters. We have m, which represents the Komar mass of the spacetime, and we have a minimal length scale L introduced to regularize the spacetime. We can see that when L goes to 0, immediately we retrieve the Schwarzschild metric, which is singular at the center. And to generate such geometry, one has to use an NED Lagrangian of this form that depends on an extra parameter alpha and the field strength F that we saw that depends on the magnetic charge previously. So this NED Lagrangian generates a geometry that has A, alpha, and Qm. And we can identify these parameters so we can generate the Hayward model. A rather unpleasant feature of this geometry is that the weak field limit is not the Maxwell limit, but it's stronger than that. And this is rather unpleasant because we know that Maxwell theory is a well-established theory. And another feature that we should pay attention to is that the magnetic charge also depends on the Komar mass here. Second geometry I'm going to study is the Bardeen model, which is actually the first model that was proposed in the literature. It shares similar features as the Hayward model. We have a Komar mass n and we have a minimal length scale L to regularize the spacetime. We have an NED Lagrangian. Again, we can identify alpha and Qn to generate this geometry. And we have, again, that the weak field limit is stronger than the Maxwell. Since these two models have this feature of having weak limits stronger than the Maxwell, I'm going to focus on the third model for demonstrating basic thermodynamic properties, which is a model that was proposed recently in the literature by Gadoni and his collaborators, I think 2022. So this model has this metric function, similar features as the other ones, but now we have a weak field limit that is the Maxwell limit. And this property is why I'm choosing this model. In all of the cases, as we see, the magnetic charge depends on the Komar mass n.
So what does that mean? Like, it means like
social matter? So the magnetic charge is an artificial way of generating these geometries, and the dependence of the Komar mass on the Komar mass will affect the first law later, and will create some extra terms that will correct the temperature. So I'll talk about this in a bit. So since I've introduced some motivation on why we should study regular black holes, and we saw how to generate these geometries, I'm going to proceed now with the study of thermodynamics. So to properly study thermodynamics, one needs to first calculate properly the thermodynamic quantities. We can use Hamiltonian formalism, or we can use Euclidean path integral formalism. Both these lead to congruent thermodynamic quantities. This is something that we proved with Phil in this paper, and basically we use the Hayward model to demonstrate this consistency between these two methods. And the first thing we are doing when we have thermodynamic quantities is to see what is the form of the first law. So E here will represent the internal energy of the system, and it will be played in these models I said before by the Komar mass. T will be the temperature, S the entropy, phi will be the conjugate potential to the minimal length scale L, which is treated as a thermodynamic variable here, and the thermodynamic volume will be the conjugate potential to the pressure, which arises by the presence of a cosmological constant. In the case of a de Sitter space-time, this is interpreted as a tension. So what we find by these two methods to obtain the thermodynamic quantities is that we have a temperature which is proportional to the surface gravity, and we have some correction terms which come from the minimal length scale L. We can calculate the potential for the thermodynamic variable lambda, and the thermodynamic volume, which is basically the usual geometric volume of the sphere, but with a correction factor. So the entropy is calculated directly from the Euclidean path integral, and it's the Bekenstein-Hawking entropy. So some comments before we proceed are why we treat the minimal length scale and the cosmological constant as thermodynamic variables. So we expect to have more fundamental theories, and we expect the minimal length and the cosmological constant to arise from vacuum excitation values of fields. As for the minimal length case, we've seen in the literature that when back reaction is accounted for, we can have varying minimal length scale. So as we'll see later on, this is not the Planck scale, it's connected to this, but it has larger value than this, and it allows to vary. Also, we see that all the couplings that appeared in the NED theories, the alpha factors we saw previously, they were dependent on L, and we've seen that in the study of thermodynamics that we had variations of coupling constant like Gauss-Bonnet theories. But the more practical reason that we can find is that without treating L and lambda as parameters, the smart formula will not be satisfied. Second thing is, why do we have a modified temperature, and if we can trust this theory to produce the thermodynamic variables. So in general, when we derive the Hawking radiation temperature, this whole derivation is heavily based on the kinematic features of this geometry. So we have that photons and gravitons moving on null geodesics. But if this is not the case, we might have some modified temperature. So this was first shown in this paper by Liberati and the rest of the people, where in Horndeski theories of gravity, which are the most general theories you can have in 4 dimensions that admit second-order differential equations of motion, they find that when we have the modified graviton velocity, then we have some modified temperature. And we saw that 4D scalar Einstein Gauss-Bonnet can also generate regular black hole geometries, and we can always find transformations to map this theory to a Horndeski theory. And when we do that, we have in the Horndeski Lagrangian terms that have the Einstein tensor coupled to covariant derivatives of the field. When this happens, we have some modified temperature. But this reasoning was proposed in this paper by Liska, Henniger, and Kubisnak, where they were studying singular geometry. But here we are studying a regular geometry, and we can make a connection between the fields and this modified temperature.
Sorry, how do you find the speed of gravity?
So there is a specific way to find the speed of gravity in the Horndeski theories, that you compare the G4 and G5 terms in the Lagrangian. So I don't remember the exact derivation of that now, but the way that you can derive that is connected to the fields that you have.
Yeah, but the normal definition of gravity on a flat space.
It's gravitational perturbation, and they calculate this. But the problem is that all geometries that we've seen, regular or singular, when we have these fields, they either diverge on the horizon or the first derivatives diverge on the horizon, and this creates problem in calculating the graviton velocity. So there's no way to say that there is consistency between the temperature we derived here and the graviton field. But this is something in the geometry. Yeah. So since we have the thermodynamic quantities, one can calculate the free energy and start studying phase transitions. So here the phase structure is studied in the case of ADS spacetime, because phase structure is mostly understood in this case. And we also restrict to the canonical ensemble, where we fix the magnetic charge. So once we combine the thermodynamic quantities, we have an equation of state that has this particular form, where it's a van der Waals-like equation of state, where the denominator here represents the reduced volume. So in the usual van der Waals studies, this represents the volume of the number of particles. And usually in the literature, when we study phase transition, what we use as reduced volume is the 2Ra's quantity. But here we see a correction term coming from the minimal length. So as for the phase structure, so we can focus on the blue curve. So on the left diagram, we have varying minimal length scale, and on the right, varying cosmological constant. We see similar features in the phase structure. So the arrows indicate the direction of increasing horizon radius. So let's say if we start with some small temperature here, and we have a mechanism of increasing the temperature, and we will reach a crossing point, and at this crossing point, the system will choose to minimize the free energy, so it will move downwards. So from a small black hole, we go to a large black hole, and this is a first-order phase transition. So we see that the Hawking phase transition is absent in this case. And this is inherently linked to the presence of a minimal length scale, L. So taking the crossing points here and combining all of them, we get a coexistence line, and this line will terminate at the black dots, which represent critical points, and these critical points are second-order phase transitions. And when we have critical points, one usually studies the behavior of thermodynamic quantities near this critical point and compares them to the mean field theory. So we have 4 exponents. The first one, every behavior is being studied with the reduced temperature. So the reduced temperature is defined the deviation of the critical temperature. And for the heat capacity, it scales with the exponent alpha. And we find that the heat capacity is independent of the temperature, when we can identify alpha being 0. The second exponent is a bit more tricky to find because it's very difficult to solve analytically because this requires to find the reduced volume for large and small black holes at the coexistence point. And to do that, we need to solve 5th order equations. So instead of that, we fit numerically here, and we see that the blue dots that represent the difference of this volume scale exactly as beta being 1/2. The isothermal compressibility scales with the coefficient with the exponent gamma. We can find this analytically going through the horizon radius. We find that gamma is 1. And as for the difference between the pressure and the critical pressure with respect to the difference between the volume and the critical volume, we find that delta is 3, and these are the usual mean field theory exponents. What is interesting though is that despite the fact that we have these critical exponents being the same as the mean field theory, we have a deviation for the mean field theory critical ratio. So usually in the mean field theory, we have a critical ratio which is calculated by a combination of the critical pressure, the reduced volume, and the temperature, and we find that it's 3/8. So these 3 models admit different corrections to the asymptotic behavior, and this is inherently linked to the way we choose to smooth the singularity. So for the Hayward model, we see corrections of order R⁻⁴, which are weak corrections. Bardeen has slightly stronger, and the strongest one are exhibited by the Cadoni model, which is R². We see that the mean field theory ratio deviation gets larger as the deformations from the geometry become larger. So the way we choose to regularize the singularity has some effect on the deviation from the mean field theory ratio, while the critical exponents for all these 3 models remain the same as the ones in mean field theory. And some comments here about the minimal length scale L and how we can actually observe that. So in this paper by Cadoni in 2022, when they presented the model I've used today, they found that we can have deviations from the perihelion angle and that scale linearly with L. So they can make some observations and constrain L and see if they can actually match, and we can actually have regular black holes as a possible alternative for ultra-compact objects. So here I'm going to use the assumption that we have a small cosmological constant, and I'm going to extract the thermodynamic quantities in Menicucci and use them to impose some bounds on this minimal length scale L with the mass of the object. So usually for any regular black hole model, we have this specific form where for some values of the minimal length scale L, we can have 2 roots, and these 2 roots will represent the inner and outer horizons. There is always a critical length which makes these 2 roots to coincide, and we have a double root, and this indicates that we have an extremal black hole. And after a certain point of the minimal length scale, we don't have any roots anymore, so the geometry now describes a horizonless configuration. So if we say that we want the object that we observe in nature to be regular black holes, that means the existence of a trapped region. So a lower bound is imposed by the requirement that these should be present and not horizonless configurations. So we have a bound, a lower bound that comes from the extremal limit. And one more bound can be imposed by the thermodynamic stability. So if we want the objects to be thermodynamically stable, then we need to have a positive heat capacity, and there is a specific point that we have a change in the sign of the heat capacity. So this imposes an upper bound for this, and we can see that the value of L will be huge since the mass of black holes is huge. So we see that the minimal length scale is not the Planck scale, but it can be larger than.
And sorry,
yeah.
By stable you mean this is a long-lived or stationary object, so it's like a big remnant. So it's not like a black hole that is has negative heat capacity but evaporates.
Yeah, here we assume evaporation.
Okay, so what is the definition of stability then?
Positive heat capacity. What do you mean? Maybe I don't understand.
No. What bothers me is most of gravitational systems have negative heat capacity. Black holes have negative heat capacity. So,
but they don't always have negative heat capacity. It depends on what parameters you have in the theory. For example, when you introduce cosmological constant.
Okay. Yeah. Cosmological constant changes the rule.
Yeah.
Yes.
I
had the symplectic reflector.
Here, the extra parameter that we have is L, and this is what changes this behavior here. If this was not the case, then, yeah. Okay. And everything I've done up to this point is static, and now we'll proceed to dynamical cases. So in dynamical cases, dynamical spacetimes, we know that we don't have time translation symmetry, so we don't have a Killing vector. But instead of that, as Pravin explained in his talk, we have a Kodama vector, and we can use the Kodama vector to extract some associated charge. The conserved charge is the missing sharp mass here. And to indicate now the time dependence, we are using the advanced coordinate V. So now the metric function is given in this particular form, where C/2 will be the missing sharp mass. And we can always find a near horizon expansion of this function, where R plus now is the horizon radius, and W1 is a linear coefficient of this expansion. So as we will see, W1 will be sufficient to demonstrate all the thermodynamic properties of dynamical regular black holes. So we showed with Sebastian that W1 is different than 0 in every regular black hole model. And as we will see in the following slide, this is inherently linked to the presence of the minimal length scale L, or if you want, the absence of a singularity. So in this case, the first law is given by this particular form, where now we have two differences with the static case. First one is that the internal energy is not played by the Komar mass, but is played by the missing sharp mass evaluated on the horizon. And the second difference is that extra terms associated with the minimal length scale L are not showing up as the conjugate potential phi, but they show up as pressure terms in the first law. The temperature is given by the Kodama surface gravity here, and this is a result of choosing the missing sharp mass as being the internal energy of the system. So to show some specific results, some specific examples, for the Hayward model, W1 of V has this form. For the Bardeen, we have this, and for the Cadoni model, we have this. As we see, in all cases, when the minimal length scale will vanish, we will have W1 being 0, no pressure terms, no contributions because of the minimal length scale L. And I will summarize now. So the absence of singularity may suggest a couple of things. We might or might not have a modified temperature. This derivation might depend on the theory we choose. So this kind of geometry should be studied further. We don't have a Hawking phase transition, and this is reminiscent of what is happening in the Reisner and Nostrom case, when we fix the electric charge and we don't allow the black hole to evaporate completely. Same thing is happening here, but we fix the magnetic charge, and this fixing the magnetic charge means that we have a minimal length scale L present. We saw that the way we choose to regularize the singularity leads to a deviation of the mean-to theory ratio, and the extent of this deviation is based on how strong the deformations are from the geometry. And the last thing we saw is that we have difference between the static and the dynamical laws. Quantities are interpreted in a different way, and extra correction terms are introduced in different ways. And I will stop here. Thank you.
Oh, actually, very well regarding the time. So questions, comments, we can even have a little. Yeah, yes, Archil.
Ask a question for clarification. Actually, so this parameter of minimal length, well, it emerges from the nonlinear theory of electrodynamics. That part of the Lagrangian, or
so here we will get the geometry from this equations of motion. We solve the field equation from the action and everything, and we get a metric that has as parameters alpha and the magnetic charge Qn. After that, we can perform an expansion of this metric function, and then we can match the parameters, and we can say that this generates this. So it's after you derive the metric coming from that, you match the parameters, and you say it generates this model.
yes, yes. So the nonlinearity in electrodynamics, that's
Here?
yes, right. So the question, so okay, so what is the typical values of L, for example? They are constrained by the constraints
Sure.
from the nonlinear electrodynamics.
If we consider the black hole in our galaxy is like 10 to the power 10 or something,
10 to the power.
which is huge, but compared to the radius of a black hole, it's like nothing. It's 10 to the 25 or something like that. I'm not entirely sure.
Sorry.
Into the yeah, meters. I think it's in meters now.
Wait a second, but from, but from flat space-time, do we have constraints? Or?
Yeah, well, nonlinear electrodynamics, what they constraint is, I mean, you know, the birefringence, no, not birefringence, but, you know, there are a lot of effects which are measured from nonlinear electrodynamics.
Sure, I prefer to see this way of generating the geometry as a fake way. I mean, we can't expect that this is an actual theory that derives regular geometries. This is a way that we can generate these geometries to study them in an effective way. I mean, if you actually believe that this is the actual theory that generates regular geometries, yeah, sure, you can study some effects and see what is happening, but I'm not entirely convinced that this is the correct theory to study.
Yeah, Archil, I mean, this can't be the right theory anyways because it doesn't have a Maxwell limit in the weak field in it. So it's
no,
just,
well,
it's
one
just
of them have, right?
Yeah, one of them you can, yeah, but again, I think it's still good to be true. And we've seen before that NET theories were not successful. And we had more fundamental theories that made predictions, so why not having the same thing here?
Okay. Thanks.
Thank you.
Hey, now it's my turn, so I don't think that I have to introduce myself. The name is on the screen. The talk is going to be quite different. In some sense, it's not all the things that I wanted to say at the last RQI after a very interesting talk of Jonathan Oppenheim, when I actually had to plead, like the pleaded court that I cannot recall. I pleaded that I cannot be certain anymore. Now I'm slightly more certain, and that's why I would like to share my doubt about quantum classical hybrids with you here today. So, well, part is also naked self-promotion. Rob Mann talked me into writing this article, review article on classical quantum hybrids for the forthcoming edition of the Encyclopedia of Mathematical Physics. So I'm going to borrow references from it, and that means if you want to see the original references, go there or go to the references that I cite. Let me start from the reasons. Why do we want quantum classical hybrids? One reason is that it's just an effective description. Say classical mechanics is hard, quantum mechanics is even harder. So if you want to simulate and describe experiments in which we have widely different scales, where at least for part of the subsystem, classical description is adequate, it's better to use it, simply because otherwise we cannot solve almost anything, including even Stern-Gerlach experiment. From the point of view of quantum fundamentalists, that's very important. If we believe or accept in some form Bohr's premise about classical experiments and classical equipment and classical language, we need to convert whatever we do, whatever is the true theory, into the classical language. And it would be nice just to have a consistent mathematical description, even if it's just a cover story from how we get quantum world to classical results. And again, at least in principle, it's definitely conceivable that, for example, general relativity, deep down there, it's classical theory. I have to admit, I don't believe in it, but beliefs, this is not what is important in physics. So if we want to look at it from theoretical perspective, we have to try to write up various classical theories and take them to the bitter end. Let me remind you, well, not so much about classical mechanics, but more about notation. So, well, we have algebra of Poisson brackets. They satisfy two very important rules, which basically almost intuitive once you begin to play with them for a while. Leibniz rule or derivative and Jacobi identity. If we have functions on the phase space, those are the way to propagate them, functions of all the positions and all the momenta. And now classical systems, or would-be classical systems, their generalized positions are x, generalized momenta are k's. Now states, Liouville density, classical probability distributions on the phase space, the normalized expectation of all the observables, which are also functions on space space, are just standard expectation values with whatever is the appropriate measure, whether it's dx, dk, or something more exotic if our phase space is more exotic. And we have the evolution equation, Liouville equation, that tells us how Liouville density evolves. And just a quick reminder, pure states in classical theory are just delta distributions in position and momentum on the phase space. Another reminder, quantum mechanics. Again, from the point of view of algebras, we do have a commuting product labeled here by a circle. We also, well, I was sort of converted into use of quantum Poisson brackets simply because many expressions that look very much more like classical, and questions about transition from quantum to classical are slightly clearer. So we take quantum commutator divided by I h bar, and that's quantum Poisson bracket. We have Heisenberg picture. Again, states, which are described, let's say, by density operators. Evolution of the density operator of a closed system is given by its Hamiltonian. So from algebraic perspective, probably a hallmark of differences between quantum and classical theory is that, yeah, we have a Poisson bracket, yeah, we have a commuting product. You know about free lunch theory, that there is no such thing as a free lunch. So we have commutative product, which is not associated. Things h bar squared popping up here. Algebras are different. Okay, now what do we want from hybrid dynamics? Well, perhaps at least minimal consistency. We want this hybrid system split into classical and quantum systems if there is no interaction. We want, with or without splitting, that marginal positive probability distributions for classical states, and we have valid density operator for quantum state. Now, again, we want each sector individually to behave in the usual way. So if we have uncoupled quantum classical system, Hamiltonian dynamics on one side, unitary dynamics on the other side, and no monkey business. And even if there is interaction, if we want to impose purely classical transformation, canonical transformations on the classical side, and say quantum unitary transformations. On the quantum side, if we have our hybrid scheme, this still should be possible. All right, now, what else we want? We want consistency with other physics. It's looks a bit like pointless or trivial list of requirements, but actually it's surprisingly strong. So we want our hybrids to satisfy the standard conservation laws if they're applicable in general. We want to consider energy to be conserved if what we describe is a closed system. We don't want superluminal communication. We don't want a violation of the second law of thermodynamics, or at least if we're so bold, then that's a testable prediction that we can violate second law of thermodynamics and hope. And well, I don't think that people are as bold as to actively promote it as a feature of a theory and not as a bug. What else we want? We really want honest, good back reaction from classical to quantum system, and that means we want quantum system to get somehow entangled with the classical one. We don't want purity of a quantum system to be constant.
Just a question on the no interaction case, splitting into classical and quantum.
Yeah.
So what if you have like a super selection rule, say with, you can't have superpositions of even and odd parity fermionic sectors. But on the classical side, fermions have mass, so they can have states associated to them.
Oh, that's fine.
So it doesn't mean the state has to separate into two.
No.
It could be direct sums.
Yes, yeah. It's just so long as you look at only if you declare that, okay, now entire system is classical, you are back to the rules of whatever is appropriate for classical system. If you want classical fermions, and it's only classical fermions, your scheme should spit out the results which you get in the standard analysis of classical fermions. At least that would be nice. And another requirement, we want honest classical limit. So if we work with very simple systems where classical and purely quantum equations of motion have the same form, we want hybrid equations to have the same form, or at least we want difference between quantum and hybrid equations of motion disappear in the limit h bar goes to 0. Now, slightly more specifically, what actually is done? Not when we look at it as a fundamental theory, but when we try to obtain it as a particular limit of truly quantum system. We have a system which would be designated as classical. We have a system which is designated as quantum. And essentially, we perform a classical limit, or at least we hand wave our way to the classical limit in one of the systems. Basically, h bar 1 goes to 0, while h bar 2 is still the h bar. Now, most of those rules appeared in a paper of Buscher and Pravin in 1988, where they were trying to systematically just summarize the rules with which people play with inflation and other cosmological scenarios in which back reaction was constantly invoked, but not at least not very well labeled. Now let me introduce a little bit of a roadmap, and because I'm not entirely sure that I will be able to present everything, once this roadmap is clear, we can stop and jump to the conclusion almost at every moment. Broadly speaking, what we have are two groups of theories. Now, there are more, but broadly, we can have, say, Hamiltonian or unitary hybrid models. And the basic premise, which I haven't specified as the additional rule, is if the entire system is actually classical, or entire system is quantum, and it's closed system. So if we have to describe it classically, Hamiltonian dynamics. If we describe it quantum mechanically, it's unitary dynamics. Then we don't want any extra stochasticity. We have a whole bunch of approaches, and that's what I'm going to talk about today for the rest of my talk. Or we do introduce stochasticity for the purposes of self-consistency, and apparently this is what happens. I think that goes at least to the works of Dioschi and Holliwell. In the recent times, it's Jonathan Oppenheim and his group who actively working on that. Essentially, the entire approach of stochastic gravity by Hu and his collaborators starts from, okay, we want classical, we want quantum, we want consistency. And this consistency apparently appears only by addition of stochasticity even into the classical sector. Now, what are the approaches? The oldest, still most useful, mean field or Ehrenfest. We have classical parameters, and we have quantum expectations affecting the classical system. We can look at the algebraic approach. We have algebras of classical operators, we have algebras of quantum operators. We want to combine them together. Let's see what can we get. And then also as more concrete realizations, there are two approaches. We can write classical mechanics as quantum mechanics on Hilbert space. That's Koopman von Neumann description of classical mechanics. It's very useful for proving all kinds of ergodic theorems and other results. If we have Hilbert space for free, let's tensor it with other Hilbert space, put the interaction, we get almost automatically some of the properties. Let's pray that we can implement other properties. That's one approach, and almost the opposite approach. We can write quantum mechanics, at least for continuous variables, as classical mechanics. We can get Wigner function, which represents density operator. We can write dynamics with the help of Moyal brackets on the phase space. Let's have quantum phase space. Let's have classical phase space. Let's try to describe the interaction. We get some other properties for free. Let's pray that everything else works out. Now, if all this fails, we have only one alternative for consistent dynamics, and that's the stochastic approach.
Suppose like any other two approaches go together?
There are additional approaches. We can say that there is some combination of mean field and Hilbert space. There's whole Reginati stochastic ensembles. There are a bit more things that I'm plotted here, but most of the properties of different classes of models and their problems appear in one or other.
Just asking because like last two approach seems like they are bound to fail because like they have like separate interactions. So and if like classical and quantum like combined, so last two approaches.
Okay, well, okay. I'm not going to scoop it very much if I say that anything beyond quadratic, and that means bilinear Hamiltonians, fails, even if people believe that it doesn't. But again, proof of absence and absence of proof are still two slightly different things. And I think we can clinch it and kill the unitary Hamiltonian models, but they're not entirely dead yet. And they're still useful, which is probably the most annoying thing. So let's start with the mean field. So our object is classically parameterized. So x, k are classical quantities. Wave function, we have classical phase space, probability distribution of the classical phase space. The equation of motion for classical variables look in a very standard way, apart from the Hamiltonian being the expectation value over all classical variables, and the dynamics Schrödinger equation. However, since the wave function depends on the classical parameters, we have to take derivatives over classical parameters. Classical parameters have dynamics. That dynamics is given by derivatives of the expectation of the Hamiltonian. Derivations are quite honest. So we start with time-dependent Hartree-Fock approximation, throw in Born-Oppenheimer, separate into fast and slow variables, expand, throw out higher order terms on the side that we want. It works. If you look at the properties, it's very nice. It separates. It's all good, but it's nonlinear. And if it's nonlinear, we can get to superluminal communications. We can get to violation of second law of thermodynamics. Also, you can see that quantum purity. It's pure state. You start with pure state, you continue with pure state. So there's no quantum classical entanglement. So we are paying a lot, and we still don't have a full-blown back reaction. When it works, it actually works pretty nicely. I just picked a couple of slides from a recent paper by the Karpusine and collaborators when they compared very loved system that people love, classical oscillator quantum qubits. We have two interacting spins. They also interact with the classical oscillator. If you do full-blown quantum simulation and then smear orbits in classical phase space, you get a nice, interesting irregular feature. You do have entanglement. You have tripartite entanglement. Obviously, you don't see it if you treat qubits oscillating on quantum background, on classical background, and even for sufficiently large value of coupling parameter, there are good qualitative agreement between this semi-classical with back reaction, which is essentially mean field approach, and full quantum approach. If we take this parameter smaller, we begin to get even quantitative singularities. So yes, that's one of the issues. It works until it doesn't, and it would be nice to have good indicators that will tell us, guys, please stop before things blow up. The only real slide about gravity, as much as we hate to admit it, this is the only thing that we can actually do fully, and that's semi-classical Einstein equation. On the left-hand side, things which are derived from classical metric. On the right-hand side, renormalization, renormalized energy momentum tensor for the matter. There are several classes of derivations, whether starting with partial various path integrals, or with writing terms on effective field theory, or Wheeler-Dewitt equation. Then we have much more hand-waving than in non-relativistic case. And actually, the honest derivation would be, okay, h bar for gravity, h bar for matter. I've done the expansion now after things which could have things which I wanted cancelled. Those that those that want, this is gravitational h bar. I put it to 0. I'm afraid that that's the most honest derivation of this thing. Wonderful thing that it works quite a lot, but it comes with interesting bunch of additional issues, starting from the question, which metric are we talking about? Because GR is nonlinear, so functions of the average and average of the functions, whether it's curvature as a function of metric, are different things. How we sit with gauge, obviously we have obvious, since Roger Penrose, obvious problems with superpositions, and that's a motivation for the stochastic gravity. And if we do perturbation theory, say around Minkowski vacuum, that turns out to be fourth order theory, and we have runaway solutions. But still, and that's an important thing to realize, when we talk about consequences of Hawking radiation and information loss paradox, discussed in any form of a quantitative way, sorry guys, that's the only framework, and that means when we look for paradoxes, those are paradoxes not about conflict between quantum mechanics and general relativity. Those are various paradoxes when we shoebox everything into this type of the equation. All right, algebras. Only one slide. This is what we want. Classical algebra, quantum algebra. Now this is the mixed bracket. If everything is classical, classical. If everything is quantum, quantum. And yeah, and I want Leibniz rule. I mean algebra. I want Leibniz rule. Well, it's not that much to ask, yeah. Well, if we want everything, we cannot have it. And it's pretty simple. We just do the expansion, stick to the usual algebraic rules, and we end up with this. And that means if B and A are not commutative, we cannot reproduce all the algebraic properties in the world that we want. Okay, let's be modest. I don't want Leibniz rule. I want only restricted Leibniz rule. Then, I think Gill and Salcedo worked out a theory, and they actually proved that for finite dimensional Hilbert space coupled to classical system, if you just require that, you can build a unique bracket that satisfies all the rest of the properties, algebraic properties. But if we look back at our table, what do we want? 1, 2, 3, 4 absolutely necessary properties. Property 2, honest density matrix, positive definite operator. In a simple model, oscillator and spins, you can come up with states which will give you negative eigenvalues for your purported density matrix. So it's gone. Now let me talk a bit about Hilbert space. Hilbert space for classical mechanics. Again, a lovely approach. We start with the Liouville equation. We just write it as an operator. The same thing that we do with Poisson brackets. We just represent it as a differential operator, stick enough i's into it, and we have Hilbert space where we can introduce classical wave function. We have observables, x and k. We have conjugate momenta which are not observable but are useful and important for dynamics. Yes, we have nice evolution, and indeed we can analyze classical mechanics in terms of functional analysis, and it's done, and it's useful for chaos. It's useful for ergodic theory, and Sudarshan and collaborator also suggested to use it as a framework to describe coupling between classical and quantum systems. If the whole purpose is to describe measurements, it works beautifully. Now, if we want unitary evolution formally, we can do it. If we want Heisenberg picture, we can do it. If we want to describe measurements a la classical, a la quantum mechanics with projection operators, we can do it. If we want entanglement, whatever it means, but at least formally, we can have it. We can also do it slightly more sophisticatedly and use analogs of gauge theory to write different forms of dynamics which will be more suitable for coupling when we describe coupling between classical and quantum systems. And indeed, it looks so obvious. We take classical Hilbert space, we tensor it with a quantum Hilbert space. Now we have a wave function. Now phase with x and q, x and k and q, maybe some other parameters if it's spin. And then we can write general evolution, Liouvillean of some form on classical side, self-Hamiltonian on the quantum side, and some coupling term. Yes, it can be done. So, for example, for such a system, using not straightforward Lagrangian Liouvillean that I showed, but something slightly more elaborated, you can get it. You can have honest evolution. You can have no problem with conservation of energy. You have, if you want, you can describe Stern-Gerlach experiment very nicely. You have unitary evolution, you have conservation of energy. Everything is nice and beautiful. So if you can, to a degree at least, describe spin and harmonic oscillator. I will say about problems in a second. If you try slightly different approach, where you insist that you do want to satisfy Jacobi identity with your interaction term, you discover perpetual motion. and you can get infinite flow of energy from a classical system to quantum system. So just a scorecard. The one that myself and Asher Perez proposed breaks down with correspondence principle, breaks down with energy. Nice gauge invariant one. It's so beautiful, but it's not positive definite. And the most disappointing for me was a paper by Demir and Werner, Hilbert space, Koopmanian mixed dynamics. Everything works. After reading for 50 pages, I realized that it works only for Gaussian states and Gaussian operators. So we do know that we can, now it's an improvement both over, let's say, my pet theory and Cesare and Dennis theory, because we do have problems even with bilinear entities. You strip classical mechanics of some of its properties, and then everything can be done. Okay, phase space. So Mayal brackets, life is good. You suspect that now harmonic oscillator should be fun, no problem, because Mayal bracket, which is a bit complicated for the thingy, for second order entities, it's just a Poisson bracket. So if you have quantum oscillator, classical oscillator, bilinear coupling, what can go wrong? So what can go wrong if you have classical oscillator and quantum oscillator?
Violent uncertainty.
Violation of uncertainty. We need not existential, epistemic, theory by Speckens, Bartlett, and Rudolph. If we boldly go like Barcella, Carvalho-Rubia, Gara, and Gomez Escalante, and couple delta distribution of classical oscillator and honest, kosher quantum the Gaussian state, and evolve them, then we can violate Heisenberg uncertainty principle. But if we throw in enough initial noise, so sufficiently kosher state, everything will be fine. And indeed, it's possible to prove that if everything is just Gaussian, then you can write classical mechanics exactly as quantum mechanics. So it's epistemically restricted classicals. An interesting thing, what happens in general. So let's try to trick our, go away from our algebraic constraints, introduce new product. In general, of course, it breaks down. We know it already. It might work for Hamiltonians of a particular form. Beautiful. But it doesn't. So if we run, again, equations of motion for this type of coupling, still reduced to Poisson brackets, and we start with kosher states, it's a particular type of kosher state, we still can violate Heisenberg uncertainty relation. So it's there. So we're going back to the questions of why to quantize gravity. One answer is if we look at it at least at the level of gravitons interacting with classical background, or gravitons interacting with classical field on Minkowski background. Bunch of harmonic oscillators, coupling above quadratic. That means we cannot do it in none of the schemes that we discussed before. So each one has a problem. So what works? Stochastic approaches, stochastic semi-classical gravity. How good are they? That's a different question. But if you want classical gravity, it's still not a theorem, but it's quite plausible that the only way of getting classical gravity quantum matter is to have stochastic theory. Thank you. Yeah.
So, quick question. With this, in the case we have the violation of uncertainty principle, Can you come up with some kind of generalized uncertainty principle which can be satisfied?
I haven't tried. Maybe. In fact, it's
is a possible.
yeah. But again, you see, point is that if we want quantum theory to behave as quantum theory, we are not allowed to introduce a generalized uncertainty relation. Because if you so it's because
well, in string theory, for example, the people find the generalization.
Oh yeah, no.
Instead of dynamics.
Yes.
Set on limits.
Yes. I think it's possible because actually to show those violations, you go for very special states and very special initial conditions. If let's say if your classical state is smeared enough, so you convert its density of its alluvial density into Wigner function. So it's wider than h bar. Then it's if you just pick random initial data, then you're not going to see this violation. You really maximize the correlations to the maximal allowed extent and.
I'm just playing the devil's advocate.
No.
That I believe.
No. Sure, no. But again, the point is that then you can say that it's not a bug; it's a feature, and then, but then, devil's advocate is that all our quantum experiments are done with classical description of the equipment, and on those experiments we see only things which are conforming to Heisenberg uncertainty relations. But yeah, but again, it's also a question is what is the price that I'm willing to pay for ability to do some sort of consistent calculation from the beginning to the end and have some reliable predictions. Okay, so I should shut up now and while Phil is filling up with the settings. So our next speaker is also our own Macquarie person, Fil Simovic, and he will tell us about Euclidean path integrals. Again, Euclidean path integrals and black holes. In a moment.
Okay, well, thank you, Danny, for the nice introduction. Thank you to everyone who's here in person and to all of us joining online today. My name is Phil. I'm a postdoc here at Macquarie with Danny Terno's group. And today I want to tell you about the Euclidean path integral, some of the nice features that it has and how we can apply it to learn things about black hole physics. I will mention some of the recent work that I did with Ioannis, which he talked about earlier today. And at the time that we did that work, we weren't really thinking about quantum information too much. So what I kind of want to do is introduce some information theoretic features to do with the Euclidean path integral and then try to reinterpret some of the results that we got in that paper in light of these types of things. So the outline of the talk is as follows. I'll mention black hole thermodynamics in general, which is the central thing that we're studying here. I'll talk about path integrals, what they are, what we can compute with them, and then discuss some various applications therein. As we know today, there's a very good reason to believe that black holes are relevant experimentally and observationally, and this will prove to be true even more so in the coming decades as observational technologies reach unprecedented levels. But for much longer, black holes have served as an important theoretical test bed to test information theory and quantum gravity. And this is because black holes seem to, despite being classical vacuum solutions to general relativity, possess thermodynamic properties. So if you believe, now Danny mentioned many alternatives to this, but if you believe that gravity should be quantized, then presumably, like other thermodynamic systems in the world, the thermodynamic description arises from some coarse graining of some microscopic degrees of freedom, which is exactly what you're trying to understand in the context of gravity. So the usual story is that variations between the mass or energy of a classical stationary black hole solution are given by a variation which looks much like the first law of thermodynamics, with kappa being the Hawking temperature and this area playing the role of the entropy. So this is one of the biggest hints, actually, that there's something strange about gravity compared to ordinary systems, and that's the entropy scales like the area and not like the volume of the system. If we want to assign a state counting interpretation to this entropy, usually this is given as a sum of the microstates that you have associated to some macroscopic quantities that define the state, and this usually scales like the volume of the system, but for a black hole, it's scaling like the area, and this tells us something about the holographic nature of gravity. In the modern covariant formulation of the first law arises from considering a flow in your phase space associated with some diffeomorphism generating vector field xi. This is in general this variation given by an integral of the symplectic current over some Cauchy surface. But now if you have a black hole background and this is a diffeomorphism generator, then this quantity evaluates to some boundary integrals at the horizon and some integrals at infinity. And these quantities are variations of the ADM mass, the angular momentum, and so on. And the quantity on the left, which is the integral of this conserved Noether charge 2 form, gives you the heat term TdS. And this S is the walled entropy. So in Einstein gravity, this is proportional to the area of the horizon, but in general, it's just the integral of this Noether charge 2 form over the horizon. And I'll come back to that walled entropy when I talk about entanglement entropy, so that's why I mentioned it here. Now let me talk a little bit about the path integral. The path integral is very nice because it provides, let's say, an alternative way to define quantum theory. Quantum theory is defined by transition amplitudes and correlation functions, and the path integral computes a transition amplitude between some initial state and some final state given by the action of a unitary time evolution operator. And formally what you do is take the action of this unitary and observe that it satisfies this very nice convolution property, which allows you to break down the evolution from the initial state to the final state into a bunch of infinitesimal sequences of steps, with epsilon being the small time difference between the initial and the final state for very large n. So you have a very large sequence of these steps given by the action of successive time evolution operators U, and what emerges is this picture of summing over all of the intermediate states that take you from the initial state to the final state, which gives you the amplitude to go from that initial to final state in the end. At each step, you insert a complete set of momentum eigenstates that you sum over, and so in the end, you get this measure for the momentum and the position eigenstates, and the Lagrangian there emerges from doing a Gaussian integration, and you have the discrete form of the path integral. And I should point out that formally the path integral is only well defined strictly when you're at this discretized level. As soon as you go to the continuum, which is the usual way that we use it, this is formally ill-defined, but nonetheless extremely useful for computing all kinds of different interesting quantities. This is what we'll use. It defines a quantum theory in the sense that it serves as a generating functional for all of the correlation functions in the theory. So you insert some fictitious current J, you take functional derivatives with respect to J, and this gives you whatever correlation functions you're interested in. This is true for a general quantum system. Another thing you can compute is the partition function, which is what I'll be working with today. And this is given by a trace of this Boltzmann factor. This Boltzmann factor is just the time evolution operator where the time interval is imaginary. So beta is minus IT. And computing the trace can be done by just summing over all paths where the initial state and the final state are equivalent and periodically identified, where the periodicity in this imaginary time is just the inverse temperature beta. So we compute the partition function for the quantum system by doing this path integral. where this exponential is now e to the minus classical action of the theory with no I. So the point is that this seems to give you very reasonable results when you apply it not to some quantum field phi, but actually the metric g. And it formally defines a quantum theory of gravity in this sense. Now, this gravitational functional measure is ill-defined in the general case. So usually what you work in is a semi-classical approximation where you argue that the Dominic contribution to this path integral comes from stationary points of the action, which are the classical solutions to the equations of motion for this action E. And you just sum over all of the classical solutions which satisfy the given boundary conditions for the problem at hand. Once you have the partition function, you can compute the mean thermal energy of the statistical ensemble that it defines, the entropy, which is what I'll focus on today, the free energy, and so on. And you can see that these quantities, you can't see, but you can show that these quantities satisfy a first law of thermodynamics for the case of black holes, equivalent to the Hamiltonian formulation where both apply. S here is that walled entropy, which I mentioned before, which is not always equal to the horizon area of a black hole. So let me talk a little bit more about entropy, because the biggest open problem, I guess, in black hole physics, one of them, is what is the nature of the entropy? What is it actually counting? What are these microscopic states? And one conjecture is that it's somehow related to entanglement entropy. So entanglement entropy arises from, you have some system, and you consider a boundary that separates two different subsystems. You partition out the one subsystem, compute the reduced density matrix, and you have entanglement, which results from ignoring the degrees of freedom on the other side of the boundary. Now, when you compute the entanglement entropy in the general case for a black hole or any other surface, it's given by the area of the surface divided by epsilon squared, where epsilon is some UV cutoff. And this is because when you compute this, you're summing over an infinite number of modes with higher and higher energy, and so this will diverge. So this looks very different than the black hole entropy, which is just A over 4 and does not diverge. And so the question is, can we understand how these are related? There's a nice result by Susskind and Blum from 1994, which shows that the entanglement entropy, when you consider the horizon of a black hole as being the boundary that partitions your two subregions, the UV divergence here is actually regulated by renormalizing Newton's constant. Okay, so what you need to do is include not the Einstein-Hilbert action, but you also need to include one-loop corrections to the Einstein-Hilbert action. These come in the form of curvature squared terms with some coefficients, and then regularizing the divergences that appear in those renormalizes the value of G, but it does so in such a way that the entanglement entropy is finite and is equal to A over 4G. But now this G is not the bare Newton's constant, it's this renormalized Newton's constant. Okay? So indeed, in this sense, the entanglement entropy can be seen as at least contributing to the black hole entropy and being finite. I'll come back to that. How do you actually compute the entanglement entropy? This is very difficult because you have to remember the trace.
This is one loop result of this normalization.
This?
Yeah.
Yes. So to actually compute the entanglement entropy is very difficult in the general case because this trace was given by a path integral, and you're taking the logarithm of some infinite dimensional matrix in the general case, and it's very hard to do. So there's an idea by Callan and Wilczek, and indeed Susskind in that paper did a similar thing, where you consider the entropy, and we're instructed here to vary with respect to beta when computing the entropy, which is the entanglement entropy. Now, in the Euclidean version of the geometry, the black hole geometry, in the general case, you have a cone with a singularity where the horizon is. Okay, and this singularity is only not present if a particular choice is made for the periodicity in imaginary time. Okay, if this is not equal to 2 pi, then you have the metric of a cone, and you have some singular geometry. In flat space, there's no horizon, and you can choose any periodicity for tau. Your metric is just R3 cross S1, and regardless of the radius of this thermal time circle, you have no conical singularity at all, and everything is fine. So things are quite subtle in the black hole case. Choosing beta to be equal to 2 pi, so that you have no conical singularity, is equivalent to just restricting yourself to the smooth Lorentzian geometry. What Callan and Wilczek did, it's called this replica trick, is to consider variations away from that smooth choice of beta, parameterized by delta. So delta is this deficit angle, which when it's 0, you have the smooth geometry. When it's non-zero, you have a cone. And they showed that this entanglement entropy that I showed before can be computed simply by considering this deficit angle, acting on the partition function, and taking the limit as this deficit angle goes to 0. And this is this replica trick, which is used commonly today in computing entanglement entropy. To prove this formula, they use the replica trick, but I don't have time to get into how exactly that works. So we'll just take it to be true for now. And just 1 year later, it was shown that this entropy is actually the same as the walled entropy when it's properly renormalized. Okay, so when you compute this quantity, the entanglement entropy, you're computing the walled entropy. There are some conditions here, some restrictions. Some of these have been lifted in the intervening years, but originally you required a bifurcated killing horizon for the entangling surface, and this would not work unless the Lagrangian is only linear in the Ricci scalar. If you had higher order terms, then these two entropies would not be equivalent anymore. Okay, so I will come back to the entanglement entropy when we talk about our regular black hole example. Now I want to talk about another nice feature of the Euclidean path integral, which is that it allows you to compute thermodynamics for black holes in asymptotically de Sitter spacetimes. So in asymptotically flat space, or de Sitter, a black hole will eventually just evaporate, so it's not at equilibrium, and so you can't really talk about equilibrium thermodynamics. Things are even more difficult in de Sitter because you have a cosmological horizon, and the temperature of that cosmological horizon is different than the black hole temperature, so there's a heat flux between the two horizons, and you don't have an equilibrium ensemble. So the idea is to put your black hole in a cavity, and you fix the temperature at the surface of the cavity, and this furnishes an equilibrium statistical ensemble. And this is accomplished exactly by taking the Euclidean path integral, which computes the partition function, but now instead of integrating over the entire manifold, which would formally diverge in asymptotically flat space or anti-de Sitter, you have some subtraction term there to regularize that. But now you just take a finite boundary, which is the cavity, and you only integrate over the interior of that boundary, and you fix the temperature at the boundary. And this gives you the partition function at that fixed temperature, whatever temperature you specify at the boundary, and then you can compute the entropy, the energy, anything else that you want with a well-defined temperature. So in the example that Ioannis mentioned earlier today, we considered this class of regular black hole solutions, which serve as a nice classical model of a regularized geometry arising from some quantum theory of gravity. As he mentioned, they're sourced by magnetic charge, so they're not physical, but they illustrate some of the nice features that we expect to arise from a regularized classical black hole geometry that we can study. And we studied this using this Euclidean path integral in asymptotically flat space, asymptotically anti-de Sitter, and de Sitter space. And one of the nice things that we showed, there is no form of the laws of thermodynamics for black holes that applies for every single type of black hole solution with every single type of asymptotic structure. You need to pick and choose which formulation you apply in which case. And especially for theories of nonlinear electrodynamics, the form of the first law is only known when you know that the gauge field inherits the symmetries of the underlying spacetime. So if you have a spherically symmetric background and a spherically symmetric gauge field, then there's a known form of the first law which holds. But in our case, we don't have that because we don't have the symmetry inheritance for the Hayward model. And so one of the nice things that we showed is that even in that case, in the absence of a proof of the form of the first law, it actually does satisfy the usual form that you expect. And furthermore, the smart relation there is linear, this, again, ordinarily relies on having this electromagnetic duality relation to prove linearity of the smart formula, and we have that here as well. As mentioned, we have...
Duality relation holds for the nonlinear case?
It does for the Hayward one, I think. Yeah. Yeah, it does in that one. But we don't have symmetry inheritance. So
regarding the symmetry on the field as of the symmetry of the space-time. So is that like people usually do, or?
People usually do, and it seems like a natural assumption, but you can come up with, even in Maxwell electrodynamics, classical solutions which do not have this property, which are nonetheless still solutions to the equations of motion. So there are known counterexamples even in that case, but most of the time you do have that. So let me not talk too much about these phase transitions, since Ioannis already mentioned that we have these variety of small to large phase transitions that ordinarily can be mapped to fluid-like transitions and have some important interpretations in holography in terms of ADS CFT. One of the notable things is that when you're in asymptotically de Sitter space, the bulk phase structure is very different than it is in asymptotically ADS. In ADS, here with negative cosmological constant, you have one second-order critical point terminating the swallowtail, and then a sequence of first-order phase transitions between a small and a large black hole occurring above some critical pressure. But in de Sitter, you have two second-order critical points which bound the region in your parameter space where you have the first-order phase transition. And so you get significantly more complicated phase diagrams, which we expect to have a lot of interesting applications in de Sitter CFT holography. So the question that I want to come back to, this is all interesting in its own right, but we computed the entropy here from the Euclidean path integral, and the question is, what entropy did we get? Because I talked about a few different ones. And the entropy we get is pi r squared. So is this the walled entropy? Is this the entanglement entropy? Well, remember that the walled entropy is always the entanglement entropy, but whether or not it only includes the classical geometric contribution to the entropy or quantum contributions from entanglement which renormalize G, this depends on what action you used. So if you included in the path integral all of those conical singular geometries, then what you obtain is the renormalized walled entropy, which contains the quantum contribution from entanglement and also the geometric contribution. In this computation, we only used the geometry with beta is equal to 2 pi, the smooth geometry at the horizon. We did not include those conical geometries, so this must be the ordinary walled entropy with the bare G. And to compute the entanglement entropy, you would have to add those higher curvature terms to the Lagrangian. So that is something that is worth doing and that we're going to work on next, is how to extract the entanglement entropy by working at the one loop effective action instead of just the tree level gravitational action to see what happens. And just to mention that the Euclidean path integral can be used in a variety of different settings to calculate interesting thermodynamic quantities for all kinds of different classes of theories and all kinds of different asymptotics for your space-time. And there's lots of interesting bulk phenomena that you can observe there. So with that, I'll end, and thank you.
Right, now it's time to ask some bitey questions.
Yes.
Not a question, yeah, very nice talk. I just wanted to mention that Geert Valley collaborators were looking for the quantum field theory systems without gravity, which has a similar saturation of the entropy, like black holes. So maybe it will be for you interesting to look from the path integral perspective of those QFTs, some of them are actually exactly solvable models, like a Grosny-View model in larger.
And they're computing entanglement entropy there.
Yeah, well, I mean, they can show that in the several limits where they exactly can compute this entropy related to the unitarity bounds in that particular case. And so those systems, as a bound state system, behave exactly the similar way as the black hole. So it's like an analogy. You may want to try all this field theoretic methods where you can use your past.
No, that sounds very interesting. I mean, the path is.
My postdoc who is now with me will be in ANU. Maybe you can talk to him.
Okay, nice. Yeah. I'm always looking for new applications, and a lot of stuff is done in just 2 dimensions. Because there you can work Gaussian, but yeah, definitely very interesting. Where did I'll end here.
Okay. We'll get Nick in a bit. So now we're taking a break from scientific talks to much more important talk. Nick Menicucci will tell us how to make friends, influence granting agencies, and get money.
Right. Okay, thank you. Now, how do I link up?
Yeah. Just connect it to your USB port. Yeah.
Okay, so I need an adapter.
It's USB-C, and those are standard ones.
Oh, that's fine. Is this?
Yeah. Then you find it in your. You find it here and run one of small exec file.
Wait, I have to.
Yeah, just open your Explorer or whatever shows your file system. And then you find it as a separate USB drive, and on it there is an exec.
Click share. Oh boy. Didn't realize I had to do all this. Oh, we're ahead of time now.
Yeah.
Okay.
Last time I tried to run it on Mac, it ended in tears.
That's okay. We'll do something else. Ready to share. Start sharing.
Okay, now it should be possible. Let's see. No, press it again.
Yeah, has to connect. Ready to share. Okay, there we go.
Yep, there we go.
All right. Ah, so it's just mirrored. Okay, cool.
Yeah, to make it to do 2 screens,
Doesn't matter.
very hard to feed.
No, this is fine. Okay, so now where should I stand?
Between the pink lines.
Between the pink lines, so I can be seen here? Yep. Okay, good. Nice setup, guys. I have some notes as well, so just a sec. And it's a 25-minute talk plus questions, yes?
Yeah.
Okay. Sync. Should we start now or wait 1 minute?
we can wait for 30 seconds.
Just enough time to get started. Okay. Oh, great. So are these being recorded?
Yeah.
Good. All right. So hi, I'm going to talk about RQI research and careers in Australia. I'm assuming that everyone knows that RQI stands for relativistic quantum information. So my research is funded through the largely through the Australian Research Council Centre for Quantum Computation and Communication Technology. I also have an Australian Research Council Future Fellowship that will start next year. International Society of Relativistic Quantum Information is an important initialism you should know, so check out their website. My research group is called CURMIT, Q-U-R-M-I-T. You can find it at curmit.org. And I work at RMIT University, which is in Australia. RMIT used to be an acronym or an initialism. It no longer is. They just call it RMIT University. All right, so first of all, who is this guy? Well, so I'm a professor at RMIT. I was born in Albuquerque into an Italian-American family. We have ravioli for Christmas, homemade ravioli. That's our standard Christmas meal. I was 25 before I realized this was not the standard American Christmas meal. I got my bachelor's degree in physics from the University of New Mexico, my hometown, 2002. And I got my PhD in theoretical physics from Princeton in 2008, although I spent 3 years of that time in Brisbane at UQ, working with Michael Nielsen and Jared Melbourne. So I got to know the Australian system pretty early. I became an Australian citizen in May 2016. And yes, you can keep your U.S. citizenship when you become an Australian. I don't know why people think you can't, but you can. So my career, I think this is important to understand. I had a lot of research fellowships. So I probably should have put there that I had research fellowships for my PhD research. That was an important component of it. And then I was a postdoctoral fellow at Pravin Institute for Theoretical Physics, which is in Waterloo, for 3 years. And then I was awarded a university postdoctoral fellowship from the University of Sydney. In fact, I was awarded a couple. I took that one. I know that ruffled some feathers. I'm sorry, guys. For 1 year of 3, and then I relinquished that one to take up an Australian Research Council fellowship, same place, in 2012. So I was at USyd for 4 years, 1 year on the research fellowship from the Union and 1 from the Australian government, and then I got a fellowship from RMIT, which came with a continuing position, and then I was promoted to associate professor in 2020, and then to professor at the beginning of this year. And starting next year, I have a future fellowship. So I had a lot of opportunities to do research, but I've also been involved in teaching and outreach and a bunch of other things. So how is this of useful to you? How is this of use to you? Well, before I say that, I will talk about, I've always had 2 research streams. So I've always had a research stream in quantum computing theory, quantum information theory, it involves quantum optics, and relativistic quantum information theory. So fundamental physics of interest to quantum and emerging quantum and relativity, sometimes just relativity, sometimes just quantum field theory, but that has relativity in it. So I've always had a more practical stream and a fundamental stream, and I think those 2 have actually helped my career quite a bit. So research career tips. So let's just start with this. So what helped me? I think looking back, I can say that obviously talent is a privilege. I'm not going to lie about that. I do have a gift for mathematics. I think most people who are doing theoretical physics have a gift for mathematics. You can do theoretical physics without exceptional mathematical skills, but you do need very good mathematical skills. And I think, though, from what I've seen in supervising students, there is a wider skill level variation than I expected that could lead to very positive outcomes. So you don't have to be the top performer to be a very good academic. In fact, sometimes that can get in the way. When you have, when you are as long as you meet some threshold of performance, It's the other things that matter. So the other things on this list. Now, privileges you often can't do anything about. I had privileges growing up because my mother worked as a teacher she was teaching computing at my primary school, and so she had access to technology in the 80s that very few other kids had access to. My dad worked as an engineer at Sandia National Labs, so he got to bring home what he thought would let us get on the internet in, say, 1996, which is way before it was available. I had opportunities at the University of New Mexico to work there, to volunteer there. So I got into technology very early, and I got into mathematics and learning about computers and all these things that stimulated the analytical side of my brain very early. I also have the race and gender privilege, or maybe I should say that's not really a privilege, that's more just like how it should be for everyone. I don't have the impediments that some other people have. But those are the starting point. The rest actually make a huge difference, and these are things that you can control. So one of them is just grit. It's just continuing through. When you face setbacks, you keep going, you work hard, you try to do the best you can and avoid discouragement. If you find yourself getting discouraged, you get help, you get assistance. Strategic decisions were very important. Thinking a few years ahead. So not just thinking, what am I going to do next? And not just thinking, whatever, it'll be fine. Thinking, what do I need to do in the next 12 months to position myself for the next 3 to 5 years? That doesn't mean that you know exactly what you're going to do in 3 to 5 years, let alone 10 or 20. But it's saying, what do I need to have done by the end of a year in order to be in a good position to have options? So it's thinking a couple years ahead and giving yourself options going forward. Professional relationships, these were incredibly important in my career, and I recommend that all of you watching and listening try to build and maintain good professional relationships. You don't need to be super popular with absolutely everyone, but what you do need to have is a few people in a variety of places, and if you can, in a variety of areas that you work well with and that you maintain those connections. Again, you don't have to go to great lengths to do this. Just travel around, meet people, talk to people about your research. Have a short little stump speech that you can say. Talk briefly and clearly about your research. Get people interested. Be willing to work with whoever you can. Don't fall into the trap of thinking that that you're better off holding a result to yourself because you might get scooped. It's almost always better to be open about your research with people that you trust or that your supervisor and mentors trust. International mobility. This was a help. I know that not everyone can do this, but if you're in Australia, going overseas, seeing how the rest of the world does quantum physics is very important. Coming back, it definitely helps having done that. If you are overseas, go to a few places, and then if you want to settle in Australia, then do that. Mentorship, extremely important. Find a good mentor. If you don't have a good mentor, get one. Because I had excellent mentorship from Michael Nielsen, and he would meet with me every couple weeks. This was after he had decided to go to Perimeter Institute. I switched primary supervisors and I was working with Jared Melbourne, but Michael stuck around, and he would guide me through, and he'd say, okay, what's interesting about your paper? What did you do in that paper? And I would get intimidated by it, but then he would say, no, just tell me. And that was really useful. Because he put things in context, and he taught me about this year by year plan. Breadth of expertise, practical and fundamental. You don't have to do both, but it does help to be able to say, okay, I'm doing this fundamental work. What are possible practical outcomes of this later on? You don't have to say that right away. If you're working on black hole physics, fine. That's very fundamental. But if you can say, look, we've never really tested quantum physics in curved spacetime. No one has done an experiment, really, to test these features. We know relativity, we know how curvature works, but we haven't done quantum-limited experiments with relativity. So this has practical implications for, say, quantum communication with satellites. That has done some of my colleagues a world of help with their applications in Australia, which I'll get to later. And fellowships and awards have been important. I got some advice from a more junior career person, and she had this great advice that she was given that said apply for basically one award every year. at least. And you should do that. Just search. It doesn't have to be big, but it goes on your CV and it builds up. So specific tips for your career: expand your expertise. Think and act strategically. I mentioned this. Travel as much as you can. If you can't, that's okay. But visit do conferences online. Invite people to visit you. Try to make connections and form and preserve those professional relationships. Those are key. Okay, so why Australia? Well, I would say that Australia is a great place to live and work. We have an excellent climate here, for the most part, unlike, say, Canada. But some people like the cold, that's okay. But we do. We have an excellent climate in the major cities. It's a safe place. We have a lot. I can, not just me, but people can walk around and feel safe in most neighborhoods in Australia even after dark. The compensation is great. I'll talk about that later. The culture, I think, is quite good. People are largely friendly. People are largely happy. The minimum wage is good. We have enough socialized medicine. I mean, it's like most other modern Western countries. Not all, but our antagonism is low, I would say. I would say that the Australian culture is quite good right now. Anyway. And the quantum research funding is excellent, especially on the technology side. So I'll talk about how that will work with RQI in a minute. So let's talk about RQI research in Australia. So first thing you need to know about Australian research is what the Australian unis are. So we say uni for university. The group of 8 are considered the most prestigious universities. They are highly ranked for research, and they have largely an academic focus. Now, there are other focuses as well, and I'll get to that in a minute. But these are the 8 universities that are top ranked on the higher education rankings. They often get the most fellowships and grants. But that doesn't mean that they're the only ones. It just means that there's a large concentration of research excellence at these places. The culture, the teaching, these things can still vary. There are people that choose to come to RMIT because of the academic culture at RMIT, as opposed to, say, University of Melbourne up the road. I don't mean to call them out. There's plenty of people that like University of Melbourne and get a lot of benefit from that. RMIT has a more technical focus. And I will move on to that to talk about the Australian Technology Network, or the ATN. This is 6 universities that focus more on practical, industry, and impact-driven research. So while on the academic metrics, we at RMIT and these other universities are not as focused on beating those citation metrics and all of that, we are focused on connecting with industry, doing things of practical importance, research contracts, having impact. So impact is beyond academia. It's not just what kind of citations are you getting. It's what are you doing outside of the academy. So this could be in helping startups. It could be in helping businesses. It could be in having an impact on government policy. And this is where the focus is for these universities, and they do quite a good job at it. At least we do, anyway. So RQI research in Australia, these are the ones that are listed on isrqi.net. We have the University of Queensland in Brisbane, we have RMIT, and we have Macquarie. So I'm first in RMIT. In Brisbane, there's Jared Melbourne and Tim Ralph. And here in Sydney, at Macquarie University, there's Danny Terno, Gavin Brennan, both who are here today. However, it's very important to understand that there is research in adjacent fields like quantum field theory, particle physics, gravity. There's a lot of fundamental research in these areas and quantum computing, quantum information happening at other universities too. I didn't want to list them because it would be way too long. But these are the ones that have declared RQI groups. So something you need to know about the Australian educational system. So if anybody is or knows someone who is thinking about going from undergrad to PhD, you need to know how the Australian educational system works, especially if you want to come here. So basically it works like this. The undergrad degrees are usually, not always, but usually 3 years. Now this is atypical compared to, say, the North American system, where it's usually 4 years. The undergraduate degree is 3 years. And then, if you want to continue on, most students will do honors, which is 1 year. I'll talk about this in a moment. But another path is a master's by research. That's 2 years. If you have either of those, you need a degree with research experience embedded. You need to have written some sort of thesis in order to be eligible for a PhD at an Australian institution. And PhDs in Australia are 3 to 4 years. They're nominally 3 years, Most students take around 3.5. Some students can take up to 4. The undergraduate degrees are very fast, only 3 years, and students specialize immediately. So you don't get to, like in the American system, where you apply to a university and then you decide which college within there you want to go to. You can mess around for a couple of years. It's a very broad education. Most Australian undergraduate degrees are fast and they're specialized from the beginning. Honours is a separate degree. It's 1 year and it includes coursework plus a research project plus writing a thesis, all in 1 year. It's quite intense. Masters by research is 2 years. It has some courses, usually, and there's a research project and a thesis. It's a longer thesis than the honors. You're not necessarily expected to. It's somewhere in between. The requirements for these theses are they increase. So this one is just some small project that you write up. This needs to be a good body of work that either summarizes the topic. Maybe it's a small new research project. PhD has to have significant new research components. In the PhD, it is also very fast by international standards. It's 3 to 4 years. Minimal coursework. Again, you specialize immediately. There's a research project plus a thesis, sometimes called a dissertation elsewhere. And there's external assessment. There's often no defense, with some exceptions by the university. No viva, sometimes it's called. Some unis are starting that, though. So undergraduate and honors, funding and scholarships. Undergraduate and honors are Aussie students, so domestic students, we call them, are supported by government loans that are repaid slowly and only after a salary threshold is met. So this is kind of nice if you're an Australian student. Unlike the American system where your student loans are due like within 1 year of finishing your degree, and you have to start paying them off regardless. You only have to start paying your HEX debt once the salary threshold is met. HEX is an acronym. That just means student loans. International students have to pay fees, tuition, and these are often quite steep. Masters by research and PhD, these are often called higher degree by research, or HDR. You'll see that acronym sometimes. These are they have government and research funded scholarships available. It's about $30K per year. So the Australian dollar is currently kind of weak. It's about 2/3 of an American dollar. I think it's comparable to the Canadian, maybe a little bit less. But that varies over time. International students have fewer scholarship opportunities and more limitations due to their visa conditions, but their fees are often waived. So international students can come in on very specialized scholarships, and it's very high-performing international students, and they get a very good education. There's a number of very good international students that have done well here. Australian academic careers. So, first of all, you need to understand how Australian unis are funded. Now, I'll tell you why that's important when we get down here. Australian universities are non-profit institutions that are partially funded by the Australian federal government. Government block grant funding, which is what I'm talking about here, is determined by the research and educational metrics. So, number of students that complete their degrees on time, research income. I don't know if it's directly publications, but I mean, there's a lot of things. Sorry?
Used to be.
Used to be, okay. So there's a lot of things that go into this formula, and it changes depending on the government. But that's basically how it is. Students pay fees or tuition that varies by the degree program. Domestic student fees are limited by law, and student loans are automatic for domestic students. International student fees are unlimited by law. They're just set by the university, and they can be quite high. This is a major source of university income to a lot of the universities in Australia. And this was a crisis during COVID because the borders were closed, and that meant that we had a lot of layoffs. There was a right-wing government at the time, and it decided not to support the universities at all. It supported some other businesses. I'm kind of bitter about it. But they decided not to support the universities, and so all universities in Australia were struggling. Most of them had significant layoffs, and we're still recovering from it, although we're coming out of it now. Government funding has been steadily decreasing in recent decades. This is a problem. And it means that Australian unis are acting like pseudo-businesses. So they're more focused on patents, more than they used to be, not more than education. They're still focused on education and research, but there's a big pitch now, especially at the non-group of 8 unis, to focus on patents, IP, contract research, and maybe even spin-offs. So this is the thing. This is another way that universities can get income. So this is kind of how you have to think about what's going on in Australia, and especially with something like RQI, which is very fundamental. It helps to frame it in this context. But I'll get to that in a moment. University positions are either continuing or fixed term. There's no formal tenure. And there's no such thing as tenure track in Australia. So just don't ask about those positions. They don't exist. But what we do have is significant protections of academic freedom and protections from firing and good conditions from the National Tertiary Education Union. Oh, my virus definitions are updated. How nice. That was supposed to be off, but whatever. The NTEU, enterprise bargaining. So join the union if you work here. There's no formal distinction between postdoc and professor. So what this means is that it still is very hard to fire people. It's just easier than in North America. There's no formal distinction between postdoc and professor. This is a huge benefit because if you arrive on a postdoc contract, you can still supervise students. You can say on your CV, I have a PhD completion. I've supervised a student. This has helped me out quite a bit on my research fellowships. So this is important. What's going on? So there's a bunch of different types of academic positions. There's casual academic. You get an hourly wage. It's very good. It's $50 plus per hour, depending on what you are doing. Variety of activities, but it's a precarious. It's not. There's no job security there. Postdoc works on someone else's grant. It's usually fixed term, 1 to 3 years usually. A research fellowship, you propose and lead your own research. This is often fixed term with some caveats. Then there's teaching and research positions, which are usually continuing positions. Continuing just means no end date with the strong, but not ultra strong like tenure protections of the enterprise bargaining agreement. Other uncommon are teaching focused positions and teaching fellowships. They do exist, but they're uncommon. So this, I think, is important, and this is one of the big benefits. Just have a look at the base salary here. So also, these numbers, you get to add an additional 17% that goes directly into your retirement account, which is called superannuation. This is a major, major draw for Australian academics to move to Australia, because these positions are great. Postdoc salaries in North America and in Europe are often shit. But here, you're on the standard level. Also of interest is that your personal title gets updated when you reach level D or level E. In other places, professor is just a job title. Here, it's a job title. Yes, that's a position title. And then there's an equivalent for research only. But professor and associate professor also replace doctor as your personal title in Australia. I was very surprised when I learned that. But it is true. So when in doubt, call someone professor, not doctor. Level A through E are the standard levels. Goes from 74 up to 201K. These are the RMIT numbers. They'll vary by university and by location. Sydney, salaries are often a little bit higher. Cost of living is higher. But there you go. So most postdocs are hired at A or B. The mid-career is usually, and the mid-career fellowships and things are usually level C. A lot of teaching and research academics start at level B or C and then work their way up through promotion. So RQI research careers in Australia. So I'm nearly done. I think I'm going to be reasonably on time. So for postdocs, remember these are working on someone else's grant, not your own. You need to start searching 12 months in advance. Now, if you have an end date of your current contract or position less than 12 months, that's okay. You'll still find something. But if you really want to maximize your opportunities, you really need to start searching early. Again, don't freak out if it's less than this. Just hustle. Set alerts at seek.com.au. That's the standard site for jobs. You can and make it broad, not just quantum, definitely not relativistic quantum information. Make it broad, make it fellowship, make it physics. Make these OR alerts, and then you'll get an email every couple days and just look through them and see what you have. Put in the cities that you want to live in: Brisbane, Sydney, Melbourne, Adelaide, Perth, Hobart, whatever you want. And other RQI or quantum-specific sites. You'll have to do your own research on that. Email the academic who has the grant. It's usually listed in the position description. Also, use your contacts. So if your supervisor knows someone, tell your supervisor, tell everyone you meet that you're looking for a position. Tell everyone you meet that you want a job. Anyone who might have possible job opportunities, ask them directly and say, look, I'm looking for a job. Don't be shy. If you want a job, go find one. Talk to people. Be persistent with academics. We often don't reply to emails. This is not personal. This is just failure to be organized. And apply directly with the university. University fellowships sometimes exist. You need to check with the individual universities. It varies over time. Some of the university fellowships that I've seen before no longer exist. Other ones have replaced them. So I'm not going to list them here. Start searching 2 years in advance for these, because these are often 1 year intake. Once a year intake, they need a lot of preparation in the application, and you need a university sponsor, so reach out early. Find someone who will say, yes, we would like to have you join our research team as an independent research leader. 1 second, let's set another timer. Almost done. Yeah, 5 minutes. Consider the university strategy. This is really important. Get help from someone locally for how to do that. I'll say more about that on the last slide. So ARC fellowships are prestigious. They're a way that a lot of people move up in their careers, and a lot of the way that people get embedded into the Australian system. So I started with a university fellowship, then I got an ARC fellowship. The Australian Research Council is the primary scientific funding agency. It's like the National Science Foundation in the US, or NSERC in Canada, or the ERC, I guess, in Europe. Start searching 2 years in advance. 2 years. Start planning 2 years ahead of time. So if your contract is 2 years, start searching now. Tell people, not searching specifically, I shouldn't have said searching, but tell people, I want a grant, I want to get a fellowship. What do I need to do now? Because there are things that you need to do in terms of writing papers, making contacts to set yourself up for that. Do visits of the places that you want to be, and start getting that going early. There's DECRAs, Future Fellowship, and Laureate Fellowship. I'll talk about that in a sec. So the DECRA is the Discovery Early Career Research Award. I put the word fellowship on the end of it. They don't call it that, but whatever. It's from 0 to 5 years from the formal date of your PhD. So actually having a later PhD grant date can be good. You have up to 2 attempts depending on your citizenship. They change this all the time. If you're Australian, you usually get more. Maybe you get 1 more attempt than other people. It's 3 years fixed term plus research funding. You need a university sponsor, so reach out early. The Future Fellowship is similar to the DECRA, but it's 5 to 15 years. There's 3 different levels depending on where you are. I recently got one at level 3. I'm at 15 years now. You have up to 3 attempts. It was my last attempt, both in terms of time and the third. So I had 2 failures before I actually got it. And there's lots of really good people that don't get one. And I know them personally. It's 4 years fixed term plus research funding, and you often get a continuing teaching and research position that you negotiate before you apply for the fellowship. You need a university sponsor. Reach out early. Laureate fellowships are for more senior people, 15 plus years. They're highly competitive, top performing senior academics from around the world. You have to fit extremely well with the university and Australian strategic priorities, and significant support from the university is expected. So I think I was done. Last slide. So tips for these fellowships and really getting yourself embedded in the Australian system. Start searching early. Tell everyone you know, I want to move to Australia, I want to get a fellowship, I want to do some research there. What do you think? How can I make that work? Visit and make connections years before applying, as early as you can. So go visit other institutions, use your supervisor's money, tack on a visit after a conference. Even a day or 2 is good. And try to make actual connections. Oh, here it is. Embed yourself within the research happening at the university via external collaboration. Say, hey, I'd like to help with this project. Don't just work on your own shit. Say, what are you working on? What can I help with? I'd really like to get involved with what you're doing. Get to know the strategy of the institution. Is it Group of 8? Is it ATN? Is it other? But find out what it is. You have to talk to people there. Get to know the Australian government priorities. So this is important. It's a bit tricky for RQI, but much of RQI can be said to benefit satellite-based quantum communication, like I said. Mention this as a long-term benefit of the basic science. Don't stress this too much because it looks like you're bullshitting, but make it clear what the technological priorities are. Consider social priorities as well. I got a grant based on saying people care about fundamental discoveries in physics, and that's a social benefit to Australia. And position yourself as more than just a researcher. If you have industry connections, that's good. If you've done teaching, that's good. If you've done outreach, supervision, etc. And that's all I have now. If you have more questions, you can email me. I should put my email, but it's my name, Nicholas.Menicucci at RMIT.edu.8. Thank you.
All right. That was nice. Just one thing to add, maybe about
Please.
applying for grants in Australia, they're ridiculously long, and you're going to get extremely frustrated.
Yeah.
And you're going to realize it's a waste of time, and it is. It's a waste of your
changing for good one.
It's a waste of your valuable time, but you can redo it. So
That's
if
true.
you don't get it,
That's true.
and you think it's good, and you've gotten good feedback, do not be shy about applying and just submitting almost the exact same thing next year.
I think that's a really good point.
You'll be amazed at how often that works.
Yeah. And I reused my university fellowship application for my DECRA. I had to put a lot more into it, but yeah, you can do that.
Yeah.
And I had some failures before I succeeded. Yeah, definitely agree with that. Any other questions? I know we don't have a lot of time.
Okay, so
That's it. Thanks.
thanks, Nick. Now that was our last morning talk. So now until 1:30, we're on lunch break.
1:45.
Oh, 45, even better.
Yeah.
Then just confirming that the schedule for the talks this afternoon is as sent by Nick, not by Nico, not by Rick this morning.
I think that the coinciding are.
All right. So, Archil, thank you all for coming back after lunch. Thanks for the break. We have Archil speaking to us now. Sorry for the mix-up on the schedule from the emails. So we're going to have to push everything back 5 minutes, and we have a new schedule which will include Archil, then myself, and then Dominic speaking until the next break. All right, whenever you're ready, thank you.
Okay, I would like to thank Danny and others from introducing me to this RQI community. I'm a particle physicist, as some of you may know, and I just wanted to talk about something that's basically is some thoughts rather than published work and so on and so forth. Just to invite the public, the quantum scientists and the relativists for discussion on this. And so the broader topic would be is how we can use quantum sensors or quantum technologies as a particle physics detectors. So since I'm a particle physicist, let me first set up my language, or at least as close as possible to others, so we understand what we are talking about. And so the prime model, or the theoretical model, actually theory, which we work with in particle physics, the standard model. As you know, this is empirically extremely successful, what you could call the fundamental description of strong, weak, and electromagnetic interactions. And behind of this experimental success, there is a even more amazing theoretical framework. This is based on relativistic local quantum field theory, and the interactions are described through the gauge invariance. So many times in previous talks on gravity, that the gauge invariance is quite important, as we understand, for the description of fundamental forces. Now, so the theory is very successful, but we also know quite well that the theory is incomplete, and there are various arguments you can hear from various people on that. One is the theoretical arguments about the construction of quantum field theory, and another is, and in particular, how we incorporate fully quantum gravity in this picture. And of course, there are observational, evidence that the theory doesn't describe everything we observe. In particular, dark matter, for example, if you think about it as the ordinary matter, is not in the standard model. Okay. Now, let me motivate what I want to, the key message here, and start with the key things about the quantum field theory. So I apologize to the expert. This is pretty, simple stuff here. So we based our observation of so-called local observables. So this the operator value fields and the product of those, and the various expectation values of these operators entering into physical observables like Hamiltonian and so on and so forth. But when you start considering already at that level, the local product of fields, you know that it's not defined, it's singular. And you can see this by reluctant non-locality, introducing some non-locality. Of course, this is a generic statement about this thing, but you can very easily evaluate that for the free fields. And you can see that this product, when you say a local limit, is divergent, and you could make sense of it. And of course, we can make sense of it with a judicious subtraction of these infinities from the physical observables that we call the procedure renormalization. You can do this not for all theories. For example, if you take gravity, and you do the same thing in there in certain limits, for example, quantization, everything goes well, but you need to do the renormalization of infinite number of parameters in your theory, which means the theory is not predictive at all. It's not the theory at all. Okay, so then you can ask the question why I just consider non-local theories. Okay, so based on non-local products of operators like this, and you can do that, and we have very successful of that kind of theory, which is not the kind of field theory, but it's a kind of string theory, which carries this basic non-locality in it. But not always, but in most cases of the discussion, you can represent these non-local operators with local operators and extra degrees of freedom added up. Okay, so that's how we think about the particle physics. Okay, so there is a theory up until the 7 valid 7 scales, and if I want to consider beyond of the scales, I have to introduce a new degree of freedom. So that's the usual thinking about. And that's how the particle physics experimentalists think about the theory. So the message is you have to resolve these apparent non-localities by depositing enough energy in a very short period of time to disturb the vacuum and produce the particles of mass m, for example. Okay, so that's what experimentalists expect. And so that's what basic thing which Rutherford told us in earlier last century, and the experiment is continuing the same way for centuries now at Large Hadron Collider, Bell 2, and other experiments, collider experiments. Now, so another thing to notice that although this is a blend of quantum and relativity together, this type of experiments, but when it comes to the particular observations, it's all the measurements are of classical quantities, like energy deposited, for example, calorimetry, or particle tracks to measure trajectories and so on and so forth, just to identify what was born in your collision. So this process, at LHC, for example, you can estimate what are the scales we are testing the theory, these ideas of relativity, and this is quite astonishing. So we're testing at other scales, essentially, if you think about the quantum mechanics and relativity. So at least in those forces, we know. Now, I usually don't talk about money, and I don't want to talk about money because that's not the issue, what I understand. But the main issue, of course, is the technological one. So, for example, if I want to go this way and test the theories of quantum gravity, I have to resolve the distances close to the Planck scale, where the quantum gravitational effect becomes important, and where I would expect to have some particle-like states produced, maybe. And to probe this type of distance scales, I have to build up with the current technology. So I have to build up a collider of the size of 10 to 10 meters. And to put it in perspective, this is 1/10 of the distance from the Earth to the Sun. Okay, so that's presumably the more major problem than the matter itself. And this is what I motivate not only myself, but there are now growing community of people in particle physics and also on quantum side who think that maybe this growing and developing quantum technologies may be the way out, or at least for certain phenomena to be tested, in a very different way. So, for example, if we measure the observables which are not directly related with local interactions. So that means that, and I can extract a certain information about the physics at the local scales. So that could be a way of doing experiments in quantum physics. In particular, measuring, for example, interference effects, the phase interference, or entanglement, which are induced by the local interactions. So, another thing about thinking about a different type of experiments is the following. So, suppose I have already particles as the cosmic relics in the universe, and they usually very rarely interact with the matter, and usually deposit very low momentum. So the momentum exchange is very small, which normal detectors cannot detect. But quantum control and manipulation can be considered actually very sensitive impulse detectors. So there are these two main things which you can think about using quantum technologies as a particle detectors. Okay, so as I said, I don't have any very particular proposals here, but I'll show some. But to illustrate the thing, let me illustrate on the way how, for example, the famous Aron bomb effect works. So here we have a typical setup of the solenoid. It's infinitely long. I don't care about the effects on the boundaries of the solenoid and of the size of A. And you know that when the electron circles around the solenoid, it becomes the Aron-Bohm phase. And Aron-Bohm phase is essentially defined by the vector potential in electromagnetics, which couples directly to the current of moving the electron. And you can obtain the result, very famous result, that the phase depends on proportional to the flux of the magnetic field through the solenoid. And this is kind of this effect, of course, can be measured then in the interference as an interference effect. And we know that this is not related to any local interaction. So obviously, because on the way of the electron essentially propagates in vacuum where the magnetic field and the resulting forces are zero. And now there is one tricky thing here. That's why the gauge invariance comes in a specific way. You may say that if Lorentz force outside of solenoid is zero and it's vacuum, and there is a gauge invariance, I can describe equivalently the physics with another gauge potential, and so the observables should be the same, which are related with my gauge potential, which include in the phase by this relation. I can choose this constant arbitrarily such that I can nullify the potential, and you may think that, okay, so the effect disappears. And of course, we know this is not the case, and this really depends on the topology of the problem. The topology obstructs taking this gauge. Okay, so the effect is real. So there are two things attached to this. Just is the gauge invariance and the topology of the space which are made up of the electron moving around the solenoid. Now, let us imagine now that the electron we considered in the previous case carries other charges. So it carries other charges, say lepton charge, which also has a carrier of, in terms of some vector boson x mu. But in this case, the vector boson is massive. Okay, let me consider this case. Of course, if you want to compute now the static potential, which is induced by the interactions which are mediated by this gauge boson, then instead of Coulomb potential, you now have this Yukawa type of potential, which is short range. And of course, this means that at large distances, these interactions are not observable. Right? So we say that the charge, new charge, which I attributed to electron, is screened right? At large distances. And here it comes, I mean, if I want to measure that charge, I have to go and resolve the distances, which is of the order of inverse quantum length of the boson which mediated force. Now, however, if I insist on the gauge invariance, and we know that the gauge invariance must be for the description of spin-bound particles, then the mass of this field has to appear through the so-called Higgs mechanism. Okay? And in the Higgs mechanism, I have two terms. Here, the mass term, which is written this way, and the term which interacts with the current of the electron with the vector field, or Lorentz invariant wave. Now, of course, in the fully gauge invariant theory, these combinations are completely equivalent. However, if there is an obstruction to the gauge invariant, then that two interactions won't be equivalent, and therefore gauge equivalent, and therefore you would expect to have, even in this kind of theory where the local charges are hidden on the screen, you would expect to have Aron of one phase. If that phase is measured in terms of a usual Aron of one phase, it has a less, it's smaller, suppressed by the 1 over mx, the mass of the boson. But nevertheless, if we can, there is no exponential suppression anymore in the phases, and therefore, if we can measure interference accurately enough, we can infer the existence of short-scale physics. And so next, I wanted to now go on another path and to talk about trapped ions as particle detectors. Now, that's not an original idea. There were recently few papers appeared when the people were discussing, for example, milli charged particles, detection of so-called milli charged particles for trapped ions. But what I want to discuss is a particular discussion of the magnetic monopoles, the detection of magnetic monopoles with the milli charged particles. Once again, the idea is the following. The key message is the following. So, suppose we have a trapped ion, which the motion of which can be very well controlled, and the quantum state is cooled down to nearly ground state. And then, suppose there is an extra particle which interacts with our trapped ion and transfers the momentum, say delta p, and you can then, if delta p, of course, is given by this relation, obviously it's a classical energy, so the ion gets excited, and if excitation is larger than omega, then you can detect those excited states. Now, if you estimate the minimum momentum which comes out of these simple relations, this is standard quantum limit, of course, relation for the momenta, and this is on the particle side is very, very low momentum transfer. Okay, so which you can, so the trapped ions can be at that simple level sensitive to very low momentum transfer. So that's the basic idea, and the rest of the talk, I just want to give you a back-and-level estimation of the sensitivity for the magnetic monopoles. Now, the magnetic monopoles, the story was introduced by Paul Dirac back in 1931, and since then they are all the time around, especially in fundamental physics, to the point that people realized something which is known as a completeness conjecture, that if we observe in nature the quantized electric charges, the complete state, completeness of the state requires the existence of magnetic charges as well. Okay, so this is the idea which goes back to Polchinski, and in most of the theories we know this is indeed true, and the reason for that is, of course, is that the electromagnetic gauge group with the quantized charge becomes compact, and the compactness of this usually means that there are monopoles as a solutions in the group. Yeah. Okay. So yes, and we have a lot of examples of this explicit solutions of the monopoles, like in grand unified theories, etc., and string theory, etc. Now, of course, we had no observation of fundamental monopoles so far, except of this Valentine Day discovery, very famous by Blas Cabrera, the only claimed discovery of the monopole. But as you know, since 2019, there was a lot of progress in condensed matter physics to show that monopole quasi-particles exist. There's an explicit demonstration for this. Oops. A few properties about the magnetic monopoles. We don't know many. It's a model dependent, but generically you can think about the magnetic monopoles having a very broad range of masses from a TeV scale. Now this is constrained from the LHC experiments up until the Planck scale, for example. That's what I would call the traditional magnetic monopole. If the masses are larger than 10 to 19, that's also possible. Then presumably they are realized as magnetically charged black holes. Okay, so I've discussed this already, some of those solutions, but this is believed to be true. Okay. Now, obviously, if this is that massive, and this is an indication coming from they are hopeless to produce it for lighters. Okay. So we need to think about some other ways to do. Now, on the other hand, this is a magnetic monopole's lowest mass in the spectrum they are stable particles because of the conservation of magnetic charge. The electron, the lowest charged particles, is stable, and therefore, if they were produced in the universe and there are mechanisms to produce them, they will be here around as a cosmic rays. Okay, so that's believed as well. Now, another very important thing about the properties is the fact that, which is very interesting now, on the quantum consistency of the existence of monopoles requires the quantization of charge. Okay, so that's where the conjecture comes from, in fact. And if you write down, so all the interactions of this monopole, of course, goes through the analog of the fine structure constant, or the magnetic fine structure constant, and of course that's huge. Okay? Because it's inversely proportional to the electric fine structure constant. Now, if we have a black holes similar, so what happens is that stability of the black holes is only in the extremal case. Okay, the extremal black hole, magnetic black holes, are stable, and so the magnetic black holes are related to the mass of the black holes divided by Planck mass to the square. Okay, so in any case, the interaction strength, which is produced, or the potential of magnetic potential, which is produced by these objects, are huge compared to the electrical objects. And you can look at the force between the ion and the monopole as the usual Coulombic force, because the change is due to the photon. It's a long-range force, and you can compare that the strength is really huge compared to the usual interaction of electrical charged particles. Now, there are, of course, a lot of searches before of these magnetic monopoles, and there are bounds on the fluxes in today's universe and in the galaxies. One of the most robust bound comes from the fact that the monopoles moving in the galaxy, they're accelerated by the galactic magnetic fields, and they get the kinetic energy from them, and they deplete the magnetic field. So, but the existence of magnetic field puts the bounds on the flux bundles of this monopole. So these are so-called very famous Bartlett bounds. But then, of course, you shouldn't overproduce those monopoles in the universe, and we have a bounce from the mass density of this monopole should be less than the matter density, the usual matter density. Okay, so these are the bounds, and if you know the bounds from the flux, then you can ask the question, very simple, back an analog calculation again, of how many of those monopoles wandering in our galaxy can reach us on Earth, And this calculation is, again, very straightforward. So these are the typical number densities in the various cases. So here I parameterize the deviation from the Parker bound as this kappa. Okay. Now we are talking about what would be the cross section of the monopole passing of a trapped ion system. And again, if you look at the geometric cross section in this case, pretty safe, it's a classical object. And you can do the estimation and find out that the effective cross section is given by this formula, which is quite large. Okay. It's mainly because of the largeness of the effective interaction with the monopoles, and also the fact that they are not very heavy, they are very slow in the virialized environment. And then you can compute the rate of how much they can interact with our ions, and these are the particular rates estimation. So this naive or very like an envelope calculation tells you that you can have an improvement over the current bound by or so, which is quite substantial. But of course, this is a very preliminary background envelope calculation. So let me conclude now with this. So I believe that the quantum technologies provide with new and in many cases unique opportunities to test the fundamental physics. And there are a lot of other areas where you can do these things. The measurement of non-local observations, like interference and entanglement, is a very important thing. You can extract the information which is otherwise unavailable for local interactions, and they're sensitive to rare events through the low recoil measurements, the like lines. The monopoles could be at some type of entanglement and so on. Thank you very much.
Yeah, thanks. I just wanted to clarify what you meant by this state relation to the monopole. What was the target of that?
Yeah, so the conjecture is the following. So if we observe in electromagnetism, for example, the electric charges which are quantized, as we do, right? So that means that the complete set of states should contain also the states with the magnetic charges.
Okay, why?
Why? That's a quantum mechanical consistency, and there is no proof. It's a conjecture,
So
which comes from the various observations and the models, but it's essentially based on the quantum consistency of the picture.
Can you get that from electromagnetic duality?
Well, yeah, I mean, if you assume the duality, that could be another thing, symmetry-based.
The discrete version.
Yes, that's right. Yes, that could be a symmetry-based argument. But yes, so there is the assumption about the electromagnetic duality. There's a lot of examples in the grand unified theories and so on, and the string constructions, which are also part of the base of the dualities, which is the base of this conjecture.
So the circumstantial evidence.
Yes.
But magnetic monopoles are required, right?
Oh, there are solutions in there.
Yeah. I mean, generic ones.
Yes.
I just was curious, like, did you get an estimate maybe talking to Mike Buchek of, like,
if I can find a mic.
Compare an event like this to a stray, patch charge field that's developed.
Yeah, I think yes, I have ongoing discussion with Mike versus lab, not directly to Mike because he's busy with other stuff, but there is a Robert Wolf there. And, yes, and in Ray, we are discussing all these things for a while now, and so we are in the stage that we have to come up with maybe some problem.
I really like this idea of saying, because we usually think, how do we make quantum technology? You're saying, how can we use quantum technologies for fundamental science? It puts it on its head. It's another way that I would think of to make a case of some sort of connection with practicality. It's universal connection.
Okay.
That could be useful for people.
Yes, the micro is very active from the cavities axiom. But many of the quantum technologies are already used.
Right.
And so, for example, one of the types of dark matter called the axons, the squeeze state is heavily used in the cavities to boost the sensitivity of the experiments. We know the LIGO and so on and so forth.
So you talked about the trapped ion and having a monopole passing through. Instead of a trapped ion, if we can have a magnetic monopole there. I've seen some work being done on black holes passing by, and have additional gravitational waves checked out. So something similar can happen with magnetic charges. Maybe we can say something about regular black holes. Is it something doable?
Yeah, I mean, one thing which I did not say, you're right. I mean, so if the interaction is large enough and there are enough magnetic monopoles, they can be trapped for some way. Okay, so one of the suggestions, for example, to look at this kind of thing is take this into heavy rocks down to the mine or something, because the density of monopoles would expect it to be more because they're trapped. Now, regarding the black holes with the interaction with the monopoles, I have to think a little bit more about this because if black hole is not charged, it's kind of largely immune. They won't just gravitational interact with the monopole, right? But if it's charged like your magnetic black hole, then it's a different story.
Well, so let's thank Archil again. Oh.
And it's some very important things.
Oh, yeah.
Yes,
It would be visible.
AIT.
Yeah, so
So our next speaker is Nicholas Funai, another visitor from down under from the south. And well, after the usual bout of technical issues, we'll be able to see him. Well, we can see him. We'll be able to see his slides. Okay, so that's the same.
how do you get full screen when you got Chrome running?
Maybe a different button to get
Okay.
the sidebar.
Oh, that's fine.
All right. Well, that will have to do. Okay. Well, hello everyone. So I'm Nicholas Funai from RMIT, and what I'm going to talk about is covariant bandlimitation in quantum field theories and its effects on the pulse. So this is the slide I always put up in front of my talks. It's basically a description of my main interest, which is how detectors or atoms interact with particular fields. And what we will find actually as a result of this particular research project is that this description is slightly too simplistic because we're sort of assuming that this is a simple task to create a particular field configuration. So what we should really what we should really be focusing on is specifically how the field created by one detector the field, so the response of the second detector. So that's basically the basis of entanglement harvesting at its core. Okay, now, what is a UV cutoff? So a UV cutoff is something which restricts the existence of particles at certain momenta. So, for example, one which we are more likely to be familiar with is if we have a field operator phi, then it's usually its standard free space notation is integral 3k and all this rubbish, and we put in this heaviside step function. And this heaviside step function tells us that we are forbidding the existence of excitations above an energy of lambda. Okay. Now, these sorts of things either appear in QT when we want to do numerical regularizations, or they appear more physically in condensed matter systems, for example, which have minimum length associated with them. And our focus really comes from the fact that if we have systems of generalized uncertainty principles, we expect them to also have minimum length, so we expect a UV cutoff to appear. But unlike condensed matter systems, we need a covariant cutoff because we're using covariant theories. So what does a covariant cutoff actually mean? Well, there is no foolproof way of defining it, but one of the ways we've chosen to define it is to say, for instance, in flat space-time, that the 4-vector k mu, the contraction of 4-vector k mu, its absolute value will be less than lambda squared. And basically that's because k mu is the only 4-vector associated with, so the only 4-vector which we can genuinely say is covariant in the QFT. Okay. So we note that when we have a non-interacting theory, sort of similar to what this is at the top, then this cutoff will do nothing because already the k0 term is already on shell with the spatial components of the k-vector, of the k4 vector. However, if we consider something like the Feynman propagator, we find the covariant cutoffs will affect the Feynman propagator, and of course Feynman propagators appear in interacting theories. So if we have a Feynman propagator which in its covariant form is written as a 4 integral over e to the I k mu x minus x prime divided by k mu k mu, the covariant cutoff will introduce a heaviside step function which truncates this integral, and that will have an effect. Okay, so that's basically a broad picture of how UV cutoffs work. Now, to give you some sort of diagrammatic context as to what this means, is on the right-hand side we have, for example, a spontaneous emission of a photon by a detector. So we have a detector in its ground state, and then at some point it spontaneously excites while emitting an excitation. Now, this excitation will be, for example, a photon. It will be on shell. That means that when you write out the 4-vector k mu, it will be omega minus k, where it follows the on-shell condition. Which means that if we apply a covariant cutoff to this system, nothing will happen. But if we apply a non-covariant cutoff, it will happen because we won't allow photons with an energy larger than lambda to exist. But if we consider on the left-hand side something more similar to what we find in entanglement harvesting protocol, where we have 2 detectors in their ground states and then they become excited by some form of communication. This squiggly line here is a virtual particle, not an on-shell photon, which means that when we apply our cutoff, we will actually have some changes taking place. But a non-covariant cutoff will have, let me rephrase that. The covariant cutoff won't have an effect on the right-hand side, but it will on the left-hand side. And so those are some of the subtleties which will appear in this problem. And it will all boil down to whenever you see a Feynman propagator, we'll just start cutting away at it. Okay. Mathematical implementations. Okay. So how the covariant cutoff actually comes about is best seen in the path into a quantization picture. And that's where most of these rules were derived, but then they follow on quite naturally into the canonical picture as well. So it boils down to sort of 2-point functions in the path integral picture, which of course are Feynman propagators. And so the covariant cutoff actually just restricts the integration domain into the path integral quantization picture. And again, that boils down to introducing this heaviside step function. It's important to note that advanced and retarded propagators will also be modified in the same way, and that's mainly because these propagators differ from the final propagator purely by non-shell property, which is unaffected by the cutoff. Now, in a canonical quantization picture, the way we would interpret this sort of idea from particle quantization is that whenever we perform Wick contractions, instead of if we have a covariant UV cutoff, this Wick contraction term here, phi x, phi y, which would normally be a final propagator, we'll just replace it with our UV cutoff final propagator. And if you want to see an alternative picture of how we would go about performing this cutoff, we could just look at the exact definition of the one of the forms of the final propagator. At least this is actually one of the retardable advanced propagators. But the introduction of a step function, which is the time ordering operation, which is inherent in the propagators, that has to be considered when you're taking the UV cutoff. So let's just ignore the part of the projection, the phi projected for now. But we expand the Heaviside subfunction into its Fourier components, and then also the 2-point function, the expectation value. And we find that between this e to the I nu t minus t prime and this e to the I minus I omega t minus t prime, those have to be considered when you're taking the covariant UV cutoff. So that's why we now have a Heaviside step function which includes omega minus nu as well as the special component of k. So that basically is the same thing as this equation 3 at the top.
Nicholas, quick question. If it's not quick, then I always used to think that we don't do this in Lorentzian signature simply because once we get to something to time-like vector which is very close to null, this is not really a restriction on anything, and that's why covariant of this form is efficient only in the Euclidean in Euclidean calculations. But probably I'm missing something.
So you don't do it?
I thought that wasn't a very useful option of introducing cutoff in Lorentzian signature, simply because you can have arbitrarily large values of energy for vectors which are very close to null.
I guess it depends what your objective is.
Oh, probably.
So you're right. It doesn't limit the energy a particle can have. But basically what it's doing in a sense is minimizing the channel capacity, as it were, of this particular operation.
Okay, so basically you don't care with its use in normal renormalization. But for the purposes of what you're interested in, it's enough.
Yeah, well, see, this is the thing. Can you is R4 in your case? Is that the Euclidean?
No. Well, that would be a Minkowski four-dimensional space. I guess the K mu would belong to a four-dimensional, 3 plus 1 dimensional Minkowski space.
R4 doesn't specify the signature. It's
yeah. Perhaps I should put 3 plus 1 instead.
The big issue is that once you move to a Lorentzian cutoff as opposed to Euclidean one, you can no longer use it as a renormalization technique.
Yeah, but basically, okay. So, but since your goals would be different, that's okay.
Yeah. So to be fair, so you say it can't be used. I haven't checked if it can be used for renormalization or not, but Dominic says
not in the usual way.
Not in the usual way. Fair enough. Basically, what we do know, so work from Cambridge Jackson Price showed us that generalized certainty principles imply, or we can derive this covariant cutoff from generalized certainty principles, which means that we're just looking at the effects of such a cutoff and see if it can be physically measured in a sense. All right, so the model we'll be using is the standard 100-to-Witt model. So we have phi as a Klein-Gordon field, and we'll just have two-level systems, two-level detectors, sigma xa and sigma x for A and B. And it's just a linear coupling strength. Chi is a switching function, so that tells us when the detector is on and off. Sigma is the monopole moment, and F is the sphere, so it tells us the detector size, whereabouts you'll be able to find and where it is influenced by the field. And just for numerical reasons, we just used Gaussians for both the switching and the smearing. strictly speaking, that means that at some point the detectors will overlap, but for numerical purposes, the overlap is small enough to be ignored. It also provides significant numerical advantages or analytical advantages. Okay, so for those familiar with entanglement harvesting, this should be more or less familiar. For those who aren't, I'll just point out some of the key features. So we start initially with detectors in the ground state and the field in the vacuum state, and following interaction we trace out the fields, and this is what the two detector reduced density matrix looks like. So it basically consists of a series of Whiteman functions on the top three lines, and then on the bottom two lines you can sort of see how we have a heaviside step function, which means that these are no longer Whiteman functions, but they're rather combinations of Feynman propagators and advanced and retarded propagators. So that means that when we implement a UV cutoff, a covariant UV cutoff, these two lines are the ones which will be affected. And so it's often also put in compressed form with this particular density matrix. For those who are familiar with that, comfortable with that. All right. So this is okay. Let me take a step back. From this density matrix, what we're going to do is we're going to compute the entanglement negativity between the two detectors. That involves taking a partial trace and then looking for any negative eigenvalues which are a result. That will be the measure we use to determine how much entanglement there is in the system. And if the negativity is 0, then because we're working with two qubits, we know that there will be no entanglement at all. Okay. So let's just clarify that. So that's what we've calculated here, more or less, is we've plotted out where the entanglement negativity is 0 and where it isn't. So if we look at this top left-hand side of the diagram, that tells us that the entanglement negativity is non-zero. So that means no matter how small it is, you can't, in theory, extract some sort of usable entanglement. On the bottom right, you can't. And these two lines, the dotted line indicates the boundary between harvesting possible and harvesting impossible when there is no cutoff. And the solid line is when there is. So you can see sort of oscillates back and forth. And if we actually just zoom in on this red box area here, which is what we've plotted on the right, you can see a little more clearly, or you can see the behavior again. It starts separating, and it just increases the range of entanglement as it works. And this effect here is actually, it's not a harvesting effect, but that just is a result of the fact that when the two detectors overlap significantly, then the major source of entanglement isn't harvesting itself, it's really just inter-detector communication. And the cutoff reduces the channel capacity there as well. So this oscillatory behavior is kind of nice because it sort of reminds us of what we see when we do a non-covariant cutoff. So the same similar sort of oscillatory behavior appears. And if we sort of just have a look at how the entanglement range increases as a function of energy gap of the detectors, we see this highly oscillatory behavior. So the solid line is once again when the cutoff is 0.1 divided by sigma t, so that's just to get to a-dimensionalize it. And the dotted line is more or less approximately twice the cutoff. And you see the characteristic that the amplitude of this oscillation halves, or more or less halves, and it's twice as frequent. So basically, you can see this will suggest the trend that will appear, which is that as the cutoff increases, these oscillations will be damped and become more frequent until basically they're non-existent.
And very high frequency.
And very high frequency, yeah. Now, I'll just show you these graphs again. So now what I want to look at is taking a slice along this axis, along this line, and showing the quantitative results of the entanglement harvesting. So instead of just showing black and 0 and 1, I'm going to show you how much entanglement negativity is along this line, as well as along this line. So for large energy gap and for small energy gap.
By the way, what's the mass of the field here?
It's a massless field. Right. Okay. So for large energy gap, we make approximately 40 times the inverse of the switching function. More or less, the behavior is unchanged. It's very subtle, the differences between them. The major differences actually appear when R, so the detector separations, is so small that again you have overlap. So that's where you see a major difference taking place. And then when you get to the point where you start seeing when harvesting becomes impossible, that's where you see the other differences taking place. Basically, between here, what that's telling us is that the main contributions to entanglement harvesting lie within the threshold of the covariant cutoff. So there's not much change. If you want to measure a difference, you have to sort of look at the boundary of entanglement harvesting range.
The cutoffs are smaller than the frequency of the insertion point, is that right?
Yep. So 0.01, 0.1, 0.2, 0.3, and the last one is 10. That sort of behaves more or less as a no cutoff.
So once your cutoff is once your cutoff is smaller than the characteristic frequency of the switching, then you just don't see it as big. I'm sorry, once your cutoff is bigger than the frequency. In other words,
yeah, I suppose you need to find a diagram to see any differences, but it'd be much less, or it'd be more challenging to see. Okay. This is basically the same diagram, but for small omega, for small energy gaps, and the reason it looks no different is actually because if we compare R, it goes up to 80. Whereas in the second diagram, it only goes up to 2, or 3. So basically, this is a consequence. This actually is more or less a description of what happens when the two detectors are overlapping rather than the effects of harvesting. Which suggests really that harvesting might not be the best place to see these effects, but rather in just communication protocols. Okay. So that's sort of a little side project I did at the as well, is does the covariant cutoff allow for subliminal signaling? So we said that it doesn't, the covariant cutoff doesn't affect free photons traveling through space, but communication between two detectors would include communication from virtual photons as well. So basically, we have the same equations running, but instead of doing the harvesting protocol, which is having the two detectors more or less simultaneous according to some observer, I'm going to put one more or less, or very close to being in the causal path of the other, and then seeing if we can get subliminal communication from there. And the way we do that basically is by saying that if Alice is the one to interact first, we trace out Alice's contribution to Bob's density matrix, and if there is any dependence on lambda A, then there's communication. So if we do that, then all these expressions up here, they're just the various contributions from Alice and Bob and so forth. But what the important details can be shown here. So depending on the initial conditions of Alice and Bob, you get some sort of magnitude contributions to the transition probabilities, but they all depend on these delta functions. So the detector separation minus the time between them. So this is basically a rewriting of Huygens Huygens principle by saying that two detectors excite each other if they lie on each other's light cones. And this additional contribution here from this SCRI term is an effect of the covariant UV cutoff, which we write here. So if we take capital lambda to go to infinity, basically these two integrals will vanish. And so knowing what this looks like will tell us a bit about how either causality or non-locality is introduced as a result of this cutoff. And this is what it looks like. For t is equal to 0, so I dependent on t, so I just let it set t to 0 and just have a look at how it looks and sort of get the oscillatory behavior as well as and it doesn't decay, so I'm bringing r times I here, so it actually decays 1.5. This oscillation is very similar to the sort of intuitively, it's very similar to the oscillations you see in a non-covariant UV cutoff taking place. So basically we see that one of the reasons why the harvesting protocol had an extended range was because we were getting superluminal communication between the two detectors in question. And that's something which has to be considered. Right. Importantly, I haven't really shown it why, but if we look at the field expectation values after the first detector interacts, the energy is positive, but the information, basically this is telling us that the information moves superluminally. So we have a disparity between the location of the energy and the location of the information, and that tells us that basically it's telling us that how we define the location of the energy needs to be changed. There's a slight flaw in trying to define the exact positions from field expectation values when you have a covariant cutoff. We should be using pure VMs, not PVMs. So basically that brings me to my conclusions that so covariant UV cutoffs only affect interactive theories because they only affect basically final propagators in offshore quantities. As a result, covariant band limits seem to improve the range of internal harvesting, which we just said is due to the superluminal behavior which introduces. Detector self-interaction seem unaffected. So if you only have one detector interacting with a field, its excitation probability, at least a second order perturbation field, I suspect high. It doesn't seem to be affected by the introduction of these cutoffs. So you need two detectors to see this effect. And as I said here, so we have a little superluminal signaling introduced by this. Now that oscillatory curve I showed you before, the graph, suggests that there may be a possibility that we could get a covariant sampling theory from it, but that's a very weak idea at the moment. It's very hopeful, but no guarantees there. Now, future work, we'll try to derive generalized concentric principles from this, and also try and resolve the issue of superluminal behavior concerning disparity between energy locations and information locations. Anyway, yeah, that's all I've got.
Questions? Dom?
Nicholas, I'm just wondering, this issue with the cutoff not affecting single detector interactions, is that just because the final data doesn't turn off for the single detector interactions?
It doesn't.
Lower order perturbations?
Yeah, it doesn't show up for lower order perturbations.
Yeah, so the model you had for the time-dependent coupling of the detector to the field, it was a Gaussian?
Yes.
But that has like infinite extents.
Right,
Past
yeah.
the future.
So
could you try something that has like
for the harvesting, that's true.
For
the harvesting, that's true. But this result, it actually has general Chi's and F's, so this is independent of that.
Okay.
Yeah.
So you consider it where you actually like literally have the field coupling to zero and stuff.
Yeah. So if I were to do that for the communication protocols I had, you would definitely see it again. Explicitly. Basically, this kernel of the interval is introducing superluminal behavior for any series and any switches. Okay. Yeah. Okay. Cool. Any questions? Right. Great. Thank you.
The same computer?
Yep. Now it's Dominic's turn.
Let's see. All right, and okay. Hi everyone. I'm Dominic. I'm a student of Nick and Nick, and this is bandlimitation, wavelets, and scale QFT to work with them done at RMIT, but also in collaboration with some people from Macquarie, namely Simon and Dan. Dan is here, Simon maybe online, but Gavin as well. And also Aki, who's probably asleep. So I just want to talk a little bit about motivation for band limitation. In the first place, Nico mentioned it a little bit just before. This is not just covariant, but non-covariant as well. But from quantum gravity, we have this notion of a maximum resolution for space-time measurement. Comes from just the thought experiment. If you combine Einstein's equations with an uncertainty principle taking GUPs, you end up with this notion that you have to have this finite minimum length scale at the end of the day. Similar thing comes from black hole thermodynamics. We talked a little bit about it this morning, and Hawking radiation, entropy. We also have this notion of it from QFT, just with regular ultraviolet cutoffs to our fields and renormalization. We have this idea that everything seems to point to this idea of a minimum length scale. And there's a question then, how can we incorporate this into our theories such that we still maybe have continuous, like notions of continuity in our QFTs, but also still have a minimum length scale as well. And regular non-covariant band limitation gives us an avenue towards this. So, just talking a little bit about band limitation from signal processing. Some of you may have heard this before, maybe multiple times. But if we have a signal, just a regular classical signal that is band limited, and thus has a finite Fourier domain, let's say symmetric, then equivalent to an ultraviolet cutoff at omega, and currently no infrared cutoff, it can be constructed from a lattice of its samples. So you can have an exact equivalence between a continuous function and a set of its, an infinite set, but still countable, of its discrete samples. And that usually comes from Shannon's sampling theorem. Here the samples are equidistantly spaced. We don't necessarily need that. They just have to be sufficiently dense over the region that you care about. The region of space, the region of space-time, depends on what you want to look at. But we can reconstruct it just with Shannon's sampling theorem or any sort of interpolation function, depending on how our samples are spaced. And this sort of thing is done commonly in animation, where you have something that's at low frequency, it's interpolated to something at higher frequency. It doesn't necessarily need to be a continuum, but we can do that. You just end up with a band-limited signal, or band-limited video, yes, in the animation case. But what it means is that we could have a discrete function and a continuous one and have them be effectively agreeable at every scale through band limitation. And what that means is we can push this idea and take normally intrinsically continuous notions such as calculus, derivatives, integrals, inner products, everything like that, and give them exact equivalent discrete representations, if only considering band-limited functions. So I just said that, but we can take the reconstruction formula, just with this S now being a sinc function, so Shannon sampling, and just take its derivative and get some equation for the derivative of a band-limited function. This is an exact derivative so long as the function remains band-limited, and it's just a linear combination of the samples. So these are just numbers, this is just the function's nth derivative at a point, and this is just its values. So you're just taking linear combinations of the function's values, and you get its derivative. And I've just said that as well. I need to figure out how this animation is going to work. But if we were to look at what this derivative looks like, it's this sort of oscillatory thing. These are these values of d, this first derivative. They decay polynomially. Turns out they're linearly for the first derivative, quadratic for the second, etc. As we keep going, they're just the polynomial decay is the power of the derivative. But you can calculate it through this. But for specific cases, they end up being these values here, which when plotted have this oscillatory behavior, but also this linear decay. Or inverse linear decay. We can do a similar thing for inner products, write a discrete equivalent to the inner product, and we find that our sinc functions are orthogonal to each other, and the result of that is that you can apply it to just the product of any two functions, any two band-limited functions under an integral, and end up with that just being the Riemann sum of their samples. So the integral of the product of two band-limited functions is just the Riemann sum of their samples. This will be useful because now we can look at that and just treat it on just the standard Klein-Gordon field and just follow the same prescription. Nico talked about it a little bit. All we end up doing is just projecting the momentum states down to only a finite region between, down to a finite band, in the same way that you might do just with some sort of projection, or just implying that any momenta beyond your cutoff just don't exist, we just don't consider it at all. The actual Fock operators, the ladder operators don't change, but the commutation relations do. We now end up with a sinc commutator instead of a Dirac delta. And if we were to take the band limit back to infinity, we would recover that Dirac delta commutation relation. It just looks like this. It's non-zero at longer ranges now, so it's no longer local. But if we look at just the integer lattice spacing, or integer multiples of lattice spacing, we still have locality if you consider only a lattice. So it's local if we only consider lattice sites. We can do the same prescription with its Hamiltonian and write it in terms of band limited fields and see that this is just derivatives and integrals of band limited functions, which we can use our techniques for, and write this as a discrete sum of the field's operators. And it's just constant momentum and the field. And we can see that we have a lattice model for the continuous quantity for the Klein-Gordon Hamiltonian. It's non-local, but it's still a lattice model. So we can sort of treat it as a lattice of coupled harmonic oscillators. Despite appearances, this spring coupling is not local. It's not even nearest neighbor. It follows that discrete derivative coupling. And so it looks a bit like this. It decays quadratically, but it's still oscillating. It's not local. There's a few things you can do to try and make it local, but if you just treat everything for now as the way it is, you end up with non-local coupling between oscillators. Again, it decays quadratically. But what it means is that if you have a band limited and continuous theory, like this one, you can always find an equivalent lattice theory that'll tell you the exact same physics. You don't have to try and interpret what this coupling sort of means, but it means that you can have just a lattice theory that gives you the same physics as the continuous one. And this actually has been looked at quite a bit, particularly in the 80s and 90s with just lattice QCD calculations that do a similar thing. But the question is, how far can we take this notion? And one of the ways is, well, can we follow a similar prescription with functions that aren't band limited, or fields that aren't band limited? Can we take them and decompose them into just a whole bunch of smaller band limited ones? And the answer is yes, we can. And we can do that with leveraging our ideas about band limited models with what we call Shannon wavelets. And this is me moving from my band limitation project to the Shannon wavelets. There you go, Dan. So, what are Shannon wavelets? They're really just another tool for functional analysis and image processing and signal processing that let us look at things in different ways. So we use them to decompose an image into different resolutions. It's image processing. Let's say, for instance, you take an image with some amount of detail and you decompose it into a high resolution, low resolution, and medium resolution components of the image, and that you could then store and later combine into the full thing later on. This is actually how JPEG image compression works. You decompose it from some sort of wavelet basis, maybe not the Shannon one, and that lets you look at different components of your image and then signal and image and signal in different regions. So in signal processing, we do the same thing. We decompose things into frequency regions, like low, medium, and high, and then you can later reconstruct the whole thing just with some sort of reconstruction formula. So let's do it with more than three. Something looks like this, with a center band here and a whole bunch of extra bands outside. So this is the band limited component with just a finite, almost ultraviolet cutoff, and a whole bunch of extra wavelet components that is the sum on the right. And all we've done here is just deconstructed the Fourier spectrum into just a whole giant sum of smaller components. So here, omega is no longer an ultraviolet cutoff, it just sets the width of each band. And then if you want to add them all back together, you just recover the whole spectrum. You've really not really changed anything, you just chopped something up to later put it back together. And the width of these bands increases for increasing scale, but that's fine. So For now, just consider it a function whose Fourier domain is only non-zero within one of these wavelets, so within these two bands. Right? So you can write it like this, and you can see that this is these two are equal, so its Fourier spectrum is only defined over the bands, and like a Shannon reconstruction formula, this will have a wavelet reconstruction. So you can write the continuous function g just as this linear combination of wavelets with its values on some sort of lattice. Psi here is the Shannon wavelet. Here again, and we can just do again reconstruction similar to Shannon, just with these new functions instead of sinc functions. They're just wavelets, which are the difference between two sincs. These coefficients are given by the values of the function on a lattice of spacing now no longer delta x, but 2 to the minus n delta x. And they're basically just the samples of g. Again, what that means is that we had a sampling theory for this banded function. And by the ability to decompose any function into a whole set of bands for its Fourier transform, you can create a sampling theory for any function, whether it's band limited or not, just by doing this decomposition and writing it in terms of its band limited component and its scaled components, each of which has a sampling theory. And that means that you can take this scaled decomposition of the function, divide it into its individual sampling theories, and then put them all back together and write a full sampling theory just for the non-band limited function. This now has it's a sum of the function samples on one lattice plus an infinite sum of its scales, different scales, at all of these different lattices of different densities. Just one thing to note, that these wavelets are orthogonal in both scale and displacement, and this similar thing, they have no overlap with the sinc function. And so
you mean discrete changes? Which what? Well, okay. In scale, you have to double it. You can't scale it continuously, right? That's not a lot.
no, it's not. This is the discrete.
Okay.
So
Discrete in scale is continuous in space, or no? Discrete in space as well.
yeah, so it's discrete in space, discrete in scale. And then through reconstruction, you can make them continuous in space, but they're still discrete in scale. But we can see that as these are all orthogonal, each component of reconstruction gives unique information about the function. So if you want to reconstruct the whole thing perfectly, you need all of these values at every scale. I might rush through this, but analogous to the band limited case, all of these wavelet decompositions at each scale has equivalence to the derivatives, both for the band limited part and the wavelet part. The coefficients are a little bit different, but they're kind of similar. They still decay polynomially with distance and position. But we can write this full generalized discrete derivative as a linear combination of the band limited functions values plus the linear combinations of the scaled functions values. This is again a fully discrete theory. It's just not one-dimensionally discrete. It's now two-dimensionally discrete. Just something we'll talk about a little bit later. For the first derivative, these look like this. They still decay linearly and they still oscillate, but now they don't cross zero. So those now seem to behave as the regular band limited. Again, follow the same prescription for the inner product and write an inner product of two functions in terms of now a whole bunch of Riemann samples on different lattices at each scale. But as we can see, there are no cross-scale terms, so you don't need any multiples of the functions in two different scales, just all at one. So we can again apply this to the Klein-Gordon field. So like a regular free scalar field, we can decompose it into different scales, and we'll see that these values are at different points in different lattices. Like so, the field values at each scale are at lattices of different spacing. So each component of the field has a sampling lattice of oscillators with spacing given by either pi on omega, which is the so that's the width of the scale, or 2 to the minus n times by the same spacing. The commutation relations are again modified, so at each scale, or at different scales, the field and its conjugate momentum always commute, but on the same scale, so phi n, again, we end up with this Kronecker delta that shows that at different scales they commute, but at the same scale they have this difference of sinks commutation relation, which is a Kronecker delta on lattice spacing, but non-local everywhere else. We do the same thing for the Hamiltonian, and we end up with a band-limited component and a scale decomposition for the rest of the modes, the rest of the frequencies. But again, there are no cross terms between scales, and because of that, we can make a few observations. First, the full non-band-limited Klein-Gordon field has this Hamiltonian, which is just the sum of all of the constituent ones, which makes sense because we've really just written the whole thing into this big orthogonal basis. The constituent band-limited and scale fields have their own respective Hamiltonians that do not have any effect on any other at any different scale. So there are no cross terms between the scales, and so each Hamiltonian on its own describes all of the physics at each respective scale and tells you nothing about everything else, and that applies for the whole theory. And so what that means is that if we recall that the band-limited Klein-Gordon field has this equivalent lattice model, well, you can, and it's a model of non-locally coupled harmonic oscillators, the same can be said for the scaled Klein-Gordon field at each level. Yep. Oh, thank you. No worries. And again, this is also a model of non-locally coupled harmonic oscillators, just with different type of coupling, still quadratically decaying. But we can now put all of these layers on top of each other to sort of try and build this two-dimensional lattice of oscillators, where now this is a dimension in our regular position that's been discretized by each cutoff, and now this is a dimension in scale. And if we wanted to naively treat this scale dimension as just another spatial dimension, we could try that. So again, we have non-local coupling between the oscillators at each scale, zero coupling between the scales, which will be important later. But the total Hamiltonian takes into account all of these 1D lattices, and so you can write the whole thing, just draw it as a 2D one, just by putting them all on top of each other. And so on each lattice, on each layer of lattice, everything is governed by the Hamiltonian at that scale. Nothing has any effect on anything else. And between the lattices, between the layers, everything behaves similarly, just with different parameters that determine how closely things are coupled to each other. Under this decomposition, the question is, can we infer the geometry of such a lattice if we were to consider scale as just another spatial dimension? And so the distance between each oscillator is set like this. It's 2 to the negative n pi or omega. And the question is, how do we quantify this cross-scale distance? And the answer is with correlation functions, or with cross-scale correlations. This is analogous to something that Akeem spoke about, I think, last year, and also a little bit in July of this year at RQI North. And there's this idea that when we consider distances, normally we would consider the metric, space-time distances. But it turns out that you can determine this metric by taking derivatives of the inverse of the Feynman propagator. It's the dimension, so it's 2 over 2 minus 4 dimensions. Inverse square of the Feynman propagator, you take its derivatives, and you end up with components of the metric. And so, if we wanted to try and infer some sort of geometry about this lattice, well, we'd have to ask ourselves, what is a correlation function between here and different points and different layers of this lattice? Again, this is just the time-ordered 2-point correlators, Feynman propagator. However, there's a problem. If we recall that the lattice has no coupling between the layers, we may also be able to note that this 2-point correlator, which will just end up taking into account an integral over the overlap over the Fourier domains of the different scales, we can note that just from this picture, there is no overlap between their Fourier domain, or basically by definition, because we use the Shannon wavelet, which requires no overlap between the scales. And so, if there's no overlap in the domains, the correlator will always be 0 when between the scales. And what does that imply? Well, it implies that we have this almost infinite separation between scales if we wanted to treat this scale as an actual distance measure. It would mean that one lattice, no matter where you draw it in a picture, would be infinitely far away from each other 1D lattice. It's like they're completely isolated. They can have no interaction with each other. And it turns out we did all this for the free field. It turns out that happens again even for interacting fields. I'm not going to get into it just time-wise. But it means that we have this notion that there's infinite distance between each layer. So, to summarize, we have perfect equivalence between discrete and continuous band-limited QFTs. Band-limited theories will always have an equivalent lattice theory, and we can decompose non-band-limited fields into band-limited ones using these wavelets, and then each of those will have their own equivalent lattice theory. There may be some applications towards defining a Lorentz covariant way of doing that so that you can have Lorentz covariant bandlimitation. I haven't thought about it too much yet. So. But you can write a non-band-limited QFT as an equivalent two-dimensional lattice model. But for Shannon decompositions, at least for Shannon wavelets, it's a little bit tricky to define distances between the layers of the lattice. For other wavelet types, it's a little bit easier. I think Shannon will talk about it this afternoon. That's right. Thank you.
So, very nice talk, interesting. Just don't quite understand. So if you have, for example, 2-point function of these fields, how does it look like? It's not analytic, or what is happening between this?
This one?
The propagator. Yeah.
So it means that if you're going to treat scale as a distance now, and make no other modifications to the mathematics, then it will be a measure of the overlap of these scales. And it just turns out that by definition, the Shannon wavelets have no overlap, whereas other wavelet types do. But for the Shannon wavelets, there can be no overlap between the.
Yeah, so there are zeros somewhere, right?
Yeah, so this will always be 0 for different scales.
But why this is analytic then? There's a function.
Can I say something? So the n and the m are not physical coordinates.
Yes.
So I think that's important to realize. This is not necessarily.
No, but that's a 2-point function eventually, right?
It is, but we have two. It's a 1 plus 1 theory. So you have 1 plus 1, and then plus a scale dimension that you just made up.
Yeah.
So there's no reason to expect that there's a Hamiltonian over this bulk space. It's definitely not a field theory over 2 plus 1 dimensional space. We have space and time and then scale.
Yep.
So, I mean, it's not analytic. You're right, it's not analytic.
Okay, yeah. Okay.
I have to think about this, but I like that you made the balls bigger for coarser scales to indicate mass renormalization.
Yes, I didn't talk about massive field, but you have to do that, otherwise it doesn't work. So.
You say that works also in interaction theory.
Yeah, so that's still 0 in interacting theory, and that's because the 2-point correlator, if you're requiring momentum conservation at the end of the day, even if you have virtual particles that aren't bounded by each individual scale, when you have, like, let's say, if you were to go to second order perturbation theory, at the end of the day, you're still going to end up with an integral that looks like this that makes the whole thing 0. So if you wanted to define something that has cross-scale terms, even if an interacting theory does have cross-scale couplings and it's Hamiltonian, the 2-point correlation function isn't going to get you towards any idea of the distance between the scales. We looked a little bit at things like 3-point correlation functions and S matrices, but it didn't get us any close because they're not local.
Dominic, did you prove that in general for all interacting theories?
Yes, we did. Oh, for all interacting theories? Yeah, not for all interactions.
For all, okay, so for scalar cosine theories, for all interactions,
Yes.
So
not just phi to the 4.
We did phi to the n. So
Okay, so not all.
No.
We did phi to the n.
Anything which is emitted at tendency.
Okay, so I guess it's thanks Dominic again. And we're going to have a break. We're starting a bit late, but we'll resume at past or at 4:45.
Yeah, 3:45.
Okay, so
Was that going to mess people up?
no, that's the same time.
It's same time, usually.
15 minutes late. So
Yeah. What did you think this was?
I just realized no one's here, like, that was 25.
What was it supposed to be?
Sorry.
What did you think it was?
USB-C and USB-C, USB. Let me welcome you to the last session for the last show of the RQI Circle for 2023. We continue one talk in person, one virtual, so it will be Zoom to broadcast. Now it will be still both our own. Dan George will talk about, he will talk about eventually, wavelets, RQI information, and all other stuff, basically continuing on the earlier discussions. So one more technical issue, two more, and we will go.
Connecting, ... Still connecting, ... Do I need to push a button?
Wait for the progress bar. It should be there, uniform.
Okay. No, you need to. Oh no, hang on. Could not connect.
Try again. I may have a newer version installed already.
Yeah, we can use my computer.
Give it a few moments. I think we should be alright.
You have all the relevant permissions.
I thought so.
What's all that?
So here we go. Connecting the base unit. Let's try again.
Yeah, take that one.
Gee, it doesn't really want to do it, does it?
Do you want to use a different laptop?
Well, we can try Denny's if this doesn't work.
Airdrop it over.
emailed it.
Okay. Yay!
Right.
Almost there. And it's okay. Let me download it. Probably it will be safer.
I don't know what's going on with this.
It's
Maybe the fact that you have a newer version is in conflict with the old documents.
okay. Okay, thinking. Can we find able to do
I have to say that considering all the stuff we have to do to get this thing going, it's been going quite smoothly.
Until now.
it? Oh, and it's Dan's fault.
Yeah, that's right. So apologies everybody.
You're the IT guy.
Yeah.
Yeah, but that's, you know.
And my number one rule when doing an event is never use click share. That being said, to be fair, I work all the point, all right up till now. So maybe it is me. Maybe I've just, you know, the click share knew somehow. But
My goodness, what the hell is going on? Okay. PDF doesn't like you. I don't know. Well, on my computer now everything is possible after it was in hands of our IT, but
So open and preview. Oh wait, yeah. No. You have a consent?
yes. Oh, finally. Finally. Victor.
Alright, you got 5 minutes left.
okay. Actually, it's not too bad because it's this probably won't fill out the whole time. I'm.
Why is Zoom on top?
Oh, Zoom's on top. Can I?
Okay.
Can I?
Yeah, kill you.
And this? No, wait, not end it.
Yeah.
Just close it.
Yeah, you can end it because okay, leave meeting.
Leave, not end. Assign a new host.
No, it's assigned.
Stop. Minimize. Just minimize.
Leave meeting.
Yeah, no, he's right. Just minimize it. Don't leave.
Assign N2 as host.
I assigned it 10 times. For God's sake.
I think every time you join, you retake it.
Oh. Yeah. Now I need to make it actually work. Okay. So. Make host. Yes. Okay.
Alright, let's try that.
Alright.
So can they hear us and see us now? Is that still happening?
Yes.
Okay, good.
Yeah.
Alright.
The Nico is mine.
Right.
Okay.
Let's go.
I'm
Full screen mode.
After a prolonged break, let's just introduce Dan again.
Yeah.
So for those on YouTube, we're going again. So let's get going, Dan.
Cool. Hi, everybody. My name's Dan. I'm a PhD student here at Macquarie with Gavin. For some reason, the up and down arrows are moving this cursor instead of the slides.
Page up, page down.
We're just getting all the luck here. There we go. I'm a PhD student at Macquarie with Gavin. This is some work that I've been working on with Gavin and Shimon, who's online from Italy at the moment. Please bear with me. It's been a little bit of a all over the place this week, so I'm just going to keep things pretty informal. Some of it towards the end is just going to be talking through some figures and things. But hopefully I can convince you that wavelets, and particularly the wavelet transform and the continuous wavelet transform, hold potential in quantum field theory for studying scale-dependent phenomena and as a renormalization tool. So, yes. No. Cool. So, motivation. We're motivated because, well, quantum field theory has a lot of scale-dependent stuff that we'd like to understand. Wavelets were introduced originally in the field of geology. We've heard about them once today already, and you'll hear about them again in Simon's talk coming after mine. It's discrete wavelet theory and continuous wavelet theory. I'll talk about both in a moment. Both of them have already shown a little bit of promise in different areas, and we wanted to know, in the case of the Casimir effect, which is just a really simple, fundamental quantum field theory type prediction or explanation, what happens when we apply a scale-dependent cutoff arising from a wavelet picture? What effect does the wavelet have? How can we tune that cutoff? How can we understand that cutoff using different types of wavelets, and how do those two things interact? So I'm going to start by talking about discrete wavelet bases, because they're a little bit easier to get your head around if you're not familiar with how wavelets operate. A wavelet basis is, you can think of it a little bit like a halfway point between a position basis and a momentum basis. It's built up of basis functions that have some localization in matter and some localization in position, as opposed to pure position or pure momenta. They're constructed, I mean, the reason why they're called wavelets is because when you draw them out, they look like a little wave. They'll some sort of squiggle, and then they taper off to zero at infinity or minus infinity. They're defined recursively, which is really interesting, in terms of a set of wavelet coefficients, like so. And in the discrete case, what we're interested in is taking integer translations of these basis functions and dyadic scalings, larger and smaller. And they're defined recursively, meaning they're defined in terms of themselves. So there's two pieces of the wavelet basis puzzle. You've got the scaling functions, which are defined in terms of themselves at smaller scales. And then you've got the wavelet function, which is defined in terms of the scaling functions at one finer scale, with a flipping sign. So in that sense, the scaling functions operate like a low-pass filter, and they effectively sum whatever your signal is. And I mean, we talk about signals because it comes from signal processing. In our case, we're more interested in a field at a position space, I suppose, rather than a signal in time space. But they're more or less equivalent. Wavelet functions operate more like a high-pass filter, taking differences. A super simple example, by the way, of a wavelet transform, a discrete wavelet transform that follows this is the Hadamard transform, where you've got the two, you've got 1, 1, 1, minus 1. The top two rows essentially sum, and the bottom two is different. So by taking that rotation, you're taking a sum and a difference of two numbers. It's a bit like taking a low pass and a high pass. So this is going to be tricky if I have to keep doing page down instead of next. So to actually calculate these things, this is the same. This expression is the same for kind of all wavelets. The way you've got this set of wavelet coefficients. What you do is you assume some sort of desirable property, and then you solve for them. So in the case of Derbyshire wavelets, you've got some number of moments that are zero, and you just assign that as an index. And then you solve for the smallest number of coefficients for which you can achieve a scaling function that has has that first number of moments equal to 0. So there's diagrams of 1, 2, 3, and 4. Derbyshire wavelets. The Haar wavelet is the k equals 1 case, and so you've got higher orders here, and they actually get smoother. And you often, in the case of the discrete wavelets, get these really nice orthonormality properties that make some of the calculations quite a bit easier. You've also got this feature where you can break down, so working as a basis, I suppose, you can take any function in L squared on R, so L2 integral functions, and you can break it down into a sum of scaling functions at some resolution or some scale, and then the wavelet functions at that scale, and then successively finer wavelet functions. We can scale limit, we implement a scale limit in that discrete picture then by cutting off all of those wavelet functions that are finer than some particular scale. For the rest of the presentation, we refer to that as capital A. Cool. Now, continuous wavelets. In the continuous wavelet picture, what we do is we take the position and scale variables that were discrete, the discrete picture, you've got the integer translations and dyadic scaling. In the continuous wavelet transform, both the scale and the translation parameters become continuous. That has a couple of implications. One of those implications is that there's no longer a scaling function, and you also don't have the concept of wavelet coefficients. What you have is you have this admissibility condition that I've put down here, whereby essentially it has to be finite. This particular integral has to be finite. And what you can do then is take any function in d dimensions, you can transform it like so, and the continuous wavelet transform essentially does this smearing, where it will take your wavelet, which functions as a kernel, convolves over all possible orientations, scales, and positions of that kernel, and then you end up with the wavelet transform. And as long as the wavelet satisfies the admissibility condition, that process is invertible. So that's sort of the illustration of what I'm talking about in terms of the action of the similitude group. Is just a fancy way of saying, yeah, we talk about that to describe translations, rotations, and scalings. Here's an example of a 1D. Again, I pinched this from a geology publication where they just generated some sample data to explain how the continuous wavelet transform looks in one dimension. If you've got a simple pure sine wave in one dimension, you can see how the continuous wavelet transform has this idea of time, in our case position, but in their case time, and scale, and you can see how the features are both localized in momenta and position.
It's really just like musical notes, isn't it?
It is, yeah. Because exactly when you play a musical note, like a piano, whatever, it starts and it stops. It doesn't go on forever in both directions. So wavelets are perfect for that sort of thing. Nope. There we go. There's also, so there's the inverse transform. So this is, when as long as it meets the admissibility condition, that C sub W will be finite, and the invertible transformation can occur. There's this nice connection between wavelets and coherent states. I recommend you go and read and have a read into that if you're interested. Yeah, I don't understand that.
Me neither.
It also preserves inner product, and in the continuous case, we go from talking about a basis. In the case of the discrete wavelet transform, you've got this exact hologram. You can do this exact mapping between before and after with quantum field theories. In the continuous case, it's a little bit more complicated. In some wavelets, we think you might be able to, if you put certain restrictions on, the scale and position, which effectively kind of discretize the continuous wavelet transform. In this case, we're just keeping it completely. We're not doing that. We're just talking about it in terms of the frame. In the continuous picture, we can scale limit the function by doing the forward continuous wavelet transform, and then when you do the reverse continuous wavelet transform, you're limiting the integration so that the scale is, instead of going from 0 to infinity, it's going from some smallest possible scale, capital A, to infinity instead. The inner product is transformed like so, and we have this addition of the function f called the cutoff function, and it's a bit hard to see what it's doing there, but in the Fourier image what you can see is that the f tilde is essentially a function of, I guess, that you're multiplying the frequency response by. So in a traditional band limit, momenta-based band limit, you've got this step function where you take all momenta up to some point and then cut it off. It's equivalent in the wavelet picture. It's equivalent to replacing that step function with something else, and that cutoff function will depend on whether the wavelet is. It might be smooth. It might taper off to infinity. It might reduce smoothly and then go to 0, or it might not reach 0, depending on how you, depending on the properties of your wavelet. yeah, sorry. So that's the inner product. That's the expression there of tilde, which is the cutoff function. Yeah. Now we looked at the Casimir effect because we were interested to see if it was a calculation that's well established. There's a set of technique. There's a regularization technique for that calculation that is quite straightforward, and we wanted to apply or see how you could do use the continuous wavelet transform to do that regularization. Now, this has already been done in 2011. Altiski and Cavaquina released a paper where they did this for a particular kind of wavelet, which is the first order emission wavelet that I'll talk about in a moment. We wanted to expand on that and say what happens if you look at higher order emission wavelets, what happens if you look at different wavelets. Can we do the general calculation, can we do the calculation not for a specific wavelet, but do it generally for any wavelet, and then be able to essentially engineer some sort of response or some sort of behavior of the Casimir force using the choice of wavelet or vice versa. So what is the Casimir effect? Just to recap, I'm sure you all know. If you take two flat conducting plates in an electromagnetic field, you restrict essentially the available modes for the vacuum energy between the two plates, so that you end up with a lower energy density between the plates versus outside, and so they're interesting together. That you experience this force that pushes them inwards, proportional to 1 less to 4. Gavin pointed out the other day that if you go kayaking, it's the same thing. If you get two people in a kayak next to each other, the waves on the outside will push the two kayaks together, which makes a lot of sense. I don't know why that hadn't occurred to me before you pointed it out. Right, so just going through some definitions for a moment. We're not using the electromagnetic field, we're just using a free complex massless scalar field. There's our Hamiltonian field definitions and equal time commutation relations, just the usual. This is before the wavelet transform. So after the wavelet transform, what we're doing is essentially applying the wavelet transform to our field operators phi hat, and then we can break that down in terms of an expression in terms of creation and annihilation operators, which are essentially the wavelet transform in momentum space of those particular operators. The commutation relations are modified, similar to the case that Dominic showed us earlier. It's a similar sort of situation. You've now got scale dependence. This is general. W can be any wavelet, so it's possible that for some particular values of things that you can get like that. I would expect that behavior that you saw with the integer spacing for the sync wavelet to show up, for example, if you start subbing that in. So
actually, that is different, though, isn't it?
No, so that is
for Shannon.
So for Shannon wavelets, that the Fourier transform of the wavelet function just gives you a whole bunch of step functions,
right?
And so the Fock ladder operators are unchanged.
Right. Because you still, okay. So the W's would be step functions or bandpass functions.
Cool. We can then express the Hamiltonian in terms of those wavelet transform creation annihilation operators, and our to actually model the Casimir effect, we're just going to impose periodic boundary conditions and then take that to infinity outside the plates and then have a finite value within the plates. So we're interested in the difference between what we're describing as, I'm getting ahead of myself, that's on the next slide. That's right. So we essentially just discretize the integral becomes a sum between the plates. We make those particular replacements. Everything from here down is pretty standard. All right, so what we want to do is calculate the energy density inside the plates using our wavelet transformed operators, and we want to impose a scale cutoff. And this is the key piece for the scale cutoff. BA is our scale cutoff essentially. S is the distance between the plates, and what we're saying is that we set all of the modes below that value A to 0. Then, here is our expression that rho naught is the energy density between the plates. And our cutoff function shows up and is equal to this. The difference between them is then given by this expression, and we can follow the same, roughly the same derivation that Casimir followed using the Euler-Maclaurin formula, and we obtain this expression here. Now, the couple of things to notice. One is the wavelet shows up here in this F tilde, so this is the cutoff function corresponding to the wavelet. If you're wondering what that relation is, I'll just jump back to here. It's that, so F tilde, the wavelet shows up in there. And you can, in some cases, you can go backwards, and I'll show you later on. We start with some wavelets that we're interested in and work out the cutoff function, and in other cases we start with the cutoff function and work back to the wavelet. I don't think we've teased out exactly whether that's possible in every circumstance. Generally, I don't think. Yeah, we don't. All right. So, yeah, a couple things. If you take the limit a to 0, you lose this term entirely, and you end up with the standard result. And for different boundary conditions, if you want to set, instead of using periodic boundary conditions, if you want to set them to 0 at the plates, it's more or less the same result, but with twice the distance. Cool, so detecting the scale cutoff. The Casimir force is given as the derivative with respect to the distance of the energy density as per usual, and we're going to consider the scale cutoff much smaller than the separation, and expand and see what correction terms we get for different wavelets. So that's an explicit expression for, again, general wavelets, and it involves the second derivative of the cutoff function. So firstly, we looked at emission wavelets, which are the same wavelets that Altiski and Kobakhidze used in their paper. The emission wavelets are the derivatives of the Gaussian. In our case, because we're operating in, we want to do the wavelet in 2 dimensions, in multiple dimensions, what we've done is define them in terms of a Fourier image, which means that we can be certain that they will meet the admissibility condition, and they're radially symmetric. The cutoff function is like so, and the lowest order correction is here. So this is consistent with Altiski and Kobakhidze when you set n equal to 1. Interestingly, for the nth emission wavelet, the first n-1 corrections vanish. So that suggests a bit like we found a similar phenomenon when we were working with discrete wavelets. But as you go to higher order wavelets, and the wavelets sort of intuitively get squigglier, you can capture more and more of that fine detail for a given particular scale. So that was an interesting find. That's the first emission wavelet, I think, in 2 or 3 dimensions. I'm not sure if that would be
emission means
no. Yes or no?
Yes. Derivatives of Gaussian.
Derivatives of
yeah, that's how you get the
yes. Yeah. Cool. And almost there. So this is a figure showing the actual force itself multiplied by the scale cutoff to make it dimensionless. So we've got the standard result here, and you can see how the higher order emission wavelets, so this is first, second, and third order, so first, second, and third derivatives of Gaussian, you essentially converge from either side, getting closer to the accepted value, which is interesting. That in the discrete case, you sort of have this trade-off, because when you're working with matrices, your squigglier higher order discrete wavelets end up require more computation to calculate. So it's sort of this computation versus accuracy trade-off, where you can end up with a sparser representation in the higher order wavelets, and I think it's a similar phenomenon here. I'm just going to talk about 3 more wavelets, and then we're done. The exponential cutoff wavelet is what we get when you work backwards from setting the cutoff function to the exponential regulator that Casimir used. So you can work backwards. In this case, if you just set it to a exponential, you get this position of momentum description. The lowest order correction is here, and it has an opposite sign compared to the expression for the first dimension wavelet. So one of the findings, I suppose, is that the corrections are not always the same sign.
So how should we understand it, in a sense? Which is
well, it's going to get weirder, Danny, when we start talking about some of the pathological wavelets, but potentially, I'm not sure. Go.
No, keep going, and then we'll talk.
Sorry, yeah, keep going. We'll talk at the end. And then the other thing is that for the exponential cutoff wavelet, you can get an exact expression for the force. And so here my slides become a little bit rougher. This is the cross section of the exponential wavelet. Again, it's sort of focused, and it had focused at the origin, and it has this very small, thin negative section that goes off to infinity. I think we're running out of time. I'm going to skip this one just to say that you can use one of the things that we can find is that you can use the wavelet-based regularization to come up with asymptotic expansions instead of series expansions from zero, so you can actually get behavior on both sides. This is the behavior, as the scale cutoff approaches the size of the separation of the plates. So that's works as well. That's a comparison of emission and exponential cutoff wavelets, showing the negative and positive. Emission, first order emission wavelet has the same sign correction. The exponential cutoff wavelet has the opposite sign correction. So yeah, that's not all that helpful with labels. Not labeled. Well, it is labeled, just not in names. It's labeled in maths.
In properties, yeah.
Yeah, done that one. All right. Two extreme wavelets. You may remember that the general correction is in terms of derivatives of the cutoff function. So the obvious question is, what happens if you find a wavelet that has a zero derivative? Such a wavelet may be non-analytic or have other weird properties, but maybe you could actually come up with a wavelet such that the Casimir effect is unchanged. We found a couple of weird things when we tried that. So here's a smooth step function for the as given. The Fourier image is like so. It looks like this. So Dominic talked about sinc functions which have a top hat and a momentum representation. This looks very similar to a sinc function, but it's smooth in the momentum representation.
And so that means they just decay faster in position.
They do, yeah. So this decays. So it decays super polynomially when calculating those derivatives. Another one is this one here, which is connected to often. I think the typical one doesn't have the 10. I think, or it might be a squared.
Curious choice.
And the 10 is there just because in order to meet the admissibility condition, it had to be that power had to be quite high. That looks like this, quite similar. And then this is both of them together. The Maya one here is the non-analytic wavelet.
So doubling of the peaks comes from what?
So what do you mean?
On previous slide. Yeah, so we have two peaks in momentum space.
Yes.
Okay.
Yeah, symmetric in position symmetry. So this was really weird. If you start picking out pathological non-analytic wavelets, you can get corrections to the Casimir force that are oscillatory. In other words, if you've got some fixed scale dependence and you change the separation of the plates, you will find that the force becomes attractive, then repulsive, then attractive, then repulsive, then attractive, then repulsive.
Well, no, it's always attractive. It's just that's the difference between the scale cutoff and the continuum limit.
Yeah, I checked that with Simon. Oh, well,
No, I'm just emphasizing that the y-axis here is the difference.
The difference. Yes, the force
scale cutoff.
Yes, but Okay, that'd be a Simon question. He might be able to answer that in his talk. But the scale here is 10 to the minus 2. The scale for the other one is 10 to the minus 4.
No, but I mean just the y-axis is a difference. Like 0 means is exactly the continuum limit.
Yeah. Oh, sorry. Yes. Okay.
So you still feel a bumpiness in the forces, right?
Potentially. Yes.
Yeah. So you could like expand your plates,
And you'll
and
feel
you'll
like
see a change of sign in the correction.
yeah, that's weird. Yeah. So it'll be easier and harder. Yeah, there'll be certain places where it's easier.
If there's a cutoff.
If there's a cutoff, that's right.
Yeah. Cool. To conclude, wavelets are great. QFT is weird, and choosing wavelets when you are investigating QFT using wavelets is quite important. Cool. Questions?
So maybe
I'll put this one up because I think that's probably the weirdest outcome there. Yeah.
So, can there be any intuitions to what, like, properties of a wavelet? Like, let's say, you wanted to have a correction. So let's say, look at the Casimir effect. You wanted to have some sort of correction that was positive based on the cutoff.
Yep.
And is there some sort of properties of the wavelet, like of the wavelet choice, that you can look for when choosing your wavelet to get those desired effects? Like, can you almost intuit what the modification of Casimir would be just from the form of the wavelets, or is it more like a case-by-case basis? You just go through each choice.
In our case, it was the latter. We just tried some things and saw what was working. I feel like you should be able to. Like there probably is a property or something that you could find that might be something to look into.
I have this more conceptual question and maybe more physics question about this. So, if you view this as a form of regularization, not changing the theory,
yes,
why the results of physical observables should be different?
I don't think. Well, I think where this becomes useful is where physical observables are themselves limited in scale. So if you're looking at an observable that is essentially scale limited, if you're using a real life detector, for example, then it may be that this becomes a useful model for modeling how that detector is going to interact with the field in this situation. But otherwise, compared to if you're talking about the results in the continuum limit, then I would expect them to be the same.
Well, my perception of regularization is just a mathematical tool to get rid of infinities.
Yeah.
Now you may have some regularization which affects your theory.
Yep.
So it's not exactly what you started with.
Yep.
And then you may have a different observable that you go check that experiment or something.
Mm-hmm.
But if it's just a regularization, I still don't understand that. It doesn't matter whether the scale dependent or whatever. If it's a physical observable, it should not depend on your mathematical manipulation to get rid of it.
Yes, I think I would agree. Yeah. I think where this turns up, so when your observable doesn't match, the other thing that occurred to us is if you've got a simulation that is essentially scale limited. So if you're modeling something, if it's a condensed matter system where you have an underlying lattice, and that the forces between that lattice have some particular characteristic that can be modeled as a wavelet, for example, it may be that the non-continuum limit of the wavelet-based theory is useful, but
in condensed matter physics, you might have a boundary condition which affects your spectrum. That could be either artifact of theory or the physical result.
Yep. Let's keep chatting afterwards.
So let's thank Dan again. And now we're going to do the most daring of the experiments today. We're going to get Shannon on Zoom and broadcast it. And we have Rick. Yeah.
Trying getting Simon's video. Post.
Shimon, you're muted still.
Oh. Still muted.
Yeah. Now we
Oh, shoot, I need to turn off the stream. Try to alrighty. Try to share my slides.
We have it yet?
no.
All right. Well, in that case, we have Simon who will be talking about
don't
this
have, I just
scalability.
have zero response. So for the third time today, I guess, I'm going to talk a bit about, well, the wavelet transform. It's going to be much shorter than Dan's introduction. So mathematicians like to call this the multi-resolution analysis or multi-scale approximation. And from the mathematics point of view, you can look at it as a sequence of nested subspaces of your square integrable functions. where you kind of have what you call a model subspace, which is subspace spanned by that scaling function, where the scaling function has this sort of renormalization property. And then you take those coefficients, right, from that renormalization equation, then you shuffle them around, and you build the wavelet function out of them. And this kind of construction ensures that those two will be orthogonal to each other. And then you kind of have a recipe to build an orthonormal basis of your square integrable functions. So you can kind of fix your, what you would call a coarsest scale, the roughest scale. And that one is kind of spanned by the scaling functions, and then your wavelet functions give you a sort of refinement in your basis. So right, yeah. So you take your scaling function and you shift it around. The same thing with the wavelets. The other option here is to kind of do a limit where you can get rid of the scaling function part and just have an orthonormal basis made of the wavelet functions at all scales. So that's also an option, which is kind of more similar to the continuous picture. And then if you have an orthonormal basis, you can kind of expand your field operators in that basis. And this provides you with a discretized version of your original QFT, where instead of a continuous space-time manifold, you now have a lattice of points, like the one on the right. You have lattice sides that have a position label and a scale label. In the figure, the scale is the radial coordinate, and the position is the angular one. And this kind of gives you the idea that when you move to finer scales, like the density of the modes is higher because they're like closer to each other, and that's why you get more and more detail. And now to get to the actual motivation is, well, Dan, Gavin, and others found out that you can sort of get a bold boundary correspondence with the wavelets. Namely, you have the boundary of some very refined degrees of freedom. That's like your boundary, and then the bulk is like this bulk I showed here, and it's all discretized, but you still can do all the fun stuff you do with the ADS-CFT correspondence, right? So one of the observations was that when you're looking at the correlation between lattice sides, they behave as if they were on an ADS manifold, right? namely that the mutual information falls off exponentially with the geodesic distance of ADS. Right? And you also have other things like the View-Tagayanaki formula. Right? So our motivation was to kind of rederive this, but with a sort of different machinery and arrive at a smooth manifold instead of like a lattice theory. So that's why we've decided to go with the continuous wavelet transform, right? And that's what we've talked about today already with Dan. It's where you make your scaling and translations continuous instead of discrete. And right, this one is just the 1D example, right, where we perform the wavelet transform in the space-like coordinate of the field. You could also imagine that you could do a sort of wavelet transform also in the time direction. We didn't really do that, but it mainly because like it's kind of tricky to work with those relativistic wavelets. Anyway, it's a possibility. We didn't go there, but you could. And yeah, that's already seen the reconstruction formula. Given that our wavelet satisfies the admissibility condition, and we can invert that. And I guess at this point, it's kind of nice to point out that since the wavelet transform is essentially acting like, well, we're smearing our field with a function, right? So our wavelet field operators may no longer be like ugly operator value distributions, might be slightly nicer, and it appears in the observation that when you look at the correlation functions for these wavelet or these scale dependent fields, the 2-point functions don't diverge when you take the coincidence limits, which is, I guess, kind of nice. And so where does the metric comes in? And that's kind of the idea that is very much popularized by Achim Kempf at the moment. And right, so the argument is, I'll do the simplest kind of argument for flat space, right? So if you have a flat space and a massless scalar field, your correlation function or the propagator for that field looks kind of like that. It's the function of distance. So you could kind of invert that relation and express the Singe world function of the flat space in terms of the propagator, right? And a quick reminder on what the Singe function is you can define it it has to be. It can be only defined between points in a convex neighborhood, so that you have a unique geodesic connecting them, and then the singe world function is the geodesic length squared, or then divided by 2 between those 2 points. And a nice thing, and the main trick of this derivation is that from the world function you can obtain the metric by this sort of differentiation. Right, you differentiate with respect to the 2 endpoints, and then you bring one of them to the other, and that gives you the metric. So in that case, you can kind of, if you know the propagator, you know the metric, right? So you could kind of argue, that's what Akim is doing, is that, well, instead of talking about manifolds and metrics, you could just talk about manifolds and 2-point functions, right? And if you're interested in that, he has a whole theory about the general or abstract endpoint function operators giving rise to space-time. But we're mainly interested in that formula for metric. So what we thought was, well, we have these correlation functions of these scale-dependent fields, where they're parameterized by 3 variables: time, position, and additionally a scale. So what happens if we think of the scale as an additional coordinate of the manifold? What kind of metric would be compatible with this correlation function, right? So yeah, we want to use that formula for those correlation functions. A nice aside is that we were mainly working with conformal fields, well, massless fields, so that, and you can use the symmetries of the field to help you greatly with these kinds of coincident limit expressions. For example, this is the coincidence of the correlation function itself, and you can use translational invariance to kind of get rid of this x, right? Because if you shift your fields by the same vector, it doesn't change anything if you have a symmetric theory, and also can kind of use the conformal symmetry of the field to simplify that, and then the coincidence limit of that correlation function just reduces to some power of the scale, depends on the scaling dimension of your field, and then you have essentially a number, right? Like it's the, what would that be? Like the yeah, it's just a number, depending on the wavelets you choose, right? Anyway, with that kind of argument, or observation, you can argue kind of this following, that if you have if you have a correlation function raised to some power and then differentiated and then taking the coincidence limit, it's going to be proportional to scale, to this power of the scale variable, and then there will be some number, some constant, which is already cool. And from that you can, that's your question, 5 minutes. From there you can compute the metric for bosons and fermions, what we did. And the main thing, right? So there are two interesting facts, right? So as opposed to the Casimir effect, where the observation changed wildly with the choice of the wavelet, here it's kind of like doesn't really depend too much on the wavelet. Like the type of geometry you get is always the same. The only thing that changes is the value of these constants alpha, beta, gamma, delta. So that's kind of the first observation, and the second is, well, which is kind of weird, is that our bosons and fermions do not seem to agree on the geometry of the scale bulk, right? And that's weird. And so our question at the moment is this discrepancy a feature or a bug, right? And our hypothesis is that it is a bug, and instead of looking at the correlation function, we should be looking at some more robust measure, like, for example, mutual information, and trying to use the mutual information to infer the metric instead of the correlation. However, well, there are some technical challenges with using mutual information. First of all, entropy in the field theory setting is a very badly behaving quantity, right? It's usually divergent, and you have to use very sophisticated mathematics to even evaluate that divergent quantity. The nice thing about all that is, well, those divergencies at least cancel out in the mutual information. So there is some hope. It's not hopeless. And then the kind of other conceptual problem that we've encountered is, if you have a discrete theory on a lattice, there is no problem with like asking what's the mutual information between two sides of the lattice. However, it's not very clear whether or not this kind of idea generalizes to the continuum limit, right? Because at least I haven't seen it in the literature, because everyone's always interested in the mutual information between regions and not between points. So that's another interesting question. And right, and so what we've been able to do so far, it also looks like that when you look at mutual information between points between points that are separated in time, you get sort of weird things. And it's also very unusual to consider this setting because all the time, whenever we talk about mutual information, it's always talking about the mutual information in a single time slice, right? We have a time slice of our lattice or our manifold, and we're looking at mutual information between regions in that single time slice. Right, and using that, there are things we've been able to do. We've been able to look at the free massless bosonic theory, which the vacuum state of that theory is a Gaussian state, so it simplifies a lot of things. And if we restrict ourselves to a single time slice and then use the mutual information, it looks like that time slice is a time slice of the ADS3 spaceline. So there is at least a hint of that supports our hypothesis that the correlations may not be the best. So yeah, to conclude, when we went from the discrete description to the continuous description, our bosons and fermions could no longer agree on the geometry of the scale bulk, and we believe the way to remedy that is to consider mutual information instead of correlations. And well, that's it for me, and thank you for entertaining the Zoom call.
Let's try. Thank you for very interesting talk. Can you try to supersymmetrize your framework and see how the fermions and bosons behave in that supersymmetrized? I mean, can you have a wavelet transforms which are explicitly supersymmetric? Where the bosons, if you take a free fermion, a Dirac fermion, and the boson with the same masses or massless, this is manifestly supersymmetric theory. It's just a simple thing. But if you also manage to have this wavelets, which keep supersymmetry, and compute the correlation function in that kind of geometry,
Oh, you mean that they are symmetric with respect to the
somehow by the supersymmetry transformations or something of that sort? I mean, at least naively.
Doesn't like supersymmetry mainly act on the internal degrees of the fields?
No, it's a space-time thing in the sense that it relates spinors with the spin zero particles, right?
To be fair, I'm not very versed in the supersymmetry theory, so
it's an interesting idea.
Maybe it's an interesting idea, of course, yes. So yeah, also other interesting ideas are we're always doing our wavelets as scalar functions. Another interesting generalization is when we are transforming our fermions, we could have spinor functions instead of scalar functions. But yeah.
Nick, can you hear me, Simon? Can you hear me okay?
Yes.
Okay, good.
Yes.
So, my question is about the philosophy of this, that you're finding a metric from a 2-point function in a bigger space,
Yeah.
right? In the scale up.
Yes.
Yeah. Right. I just want to confirm that that's correct.
Oh, that was the question. Okay.
Oh, no.
Yes,
That's
that-
the preface. I didn't hear your answer. That's all. Okay. So if
Oh,
that's the
okay.
case, then the idea of getting a metric from a 2-point function implicitly has within it that you're in some background space-time, which fine, maybe we are, but also that there's that the state that you're sampling is some reasonable state of some reasonable quantum field, I would assume. Because and so we would need to know, so that's a potential flaw in this, because we don't really have a quantum field theory on this bulk space, do we? Do we have a local Hamiltonian on this bulk space?
Well, yeah, I mean, you just do a wavelet transformation on the Hamiltonian.
But is it local in the
It's-
bulk?
That
It's,
isn't.
it's bounded local.
It's quasi-local. Okay, all right. So I wonder, so actual QFT is fully local, unless it's bandlimited, but I mean, the traditional QFT is fully local. And all the states in it are ground states of a local Hamiltonian. Because what you've got there is you've got distances that are going to zero in an only quasi-local Hamiltonian.
That is true.
So that could be a potential wrinkle in your wavelets. Pun intended.
Well, I mean, at least for the fermionic case, with the 2-point correlators, because the only thing you can measure is really field correlators for a spin form of the fermionic.
Okay.
The photons issues you get high and phi.
Right.
So we don't say it's like what I call the way to unify both pictures. But I mean, you know, we are seeing ADS metric in that case. So, and that would be consistent with the view talking about the formula. Where if you would take that metric and integrate it along the geodesic, you get a length which is proportional to the.
Yeah.
So I agree, it's still only suggestive.
I see your point though. I mean, yeah, but it is suggestive. Yeah, it is suggestive. Okay. All right, thanks.
Hey, Shimon, you should get some coffee.
Yeah, dude. Maybe an adrenaline shot.
Yeah.
Can go and start sleeping until 9.
Yeah. Thanks for coming.
Yeah.
Next time you can record it.
Yeah.
The same.
Oh, that's true, but you know, I wouldn't be able to respond to questions. Well,
Sometimes people do the recorded presentation and then they're online for questions. Anyway, something for future thoughts for people giving remote thoughts at terrible hours.
All right. Well,
Okay.
Okay.
thank you very much, and enjoy the rest of the day.
That's like, yeah, it's a different shit.
Thanks.
All right.
every answer is excited.
Yeah, that's right.
Somehow we were supposed to get Rick online. I text him.
I am definitely here. Then you want to say some words?
Hang on.
Then you can just say the final words.
It's Max.
Try again.
I'm trying again.
Okay.
Great. So I mean, thanks everyone for coming. Thanks everyone for joining. This is the last RQI circuit that happens in person. This has been a series of 6 local conferences. We had a conference in Waterloo, one in Nottingham, one in Vienna, one in Stockholm, one in Bremen. The last one is in Sydney. That's the only one that I couldn't really be present. It's kind of too far away and too expensive to go there. But still, you guys did an amazing job at showcasing the research that is being done in Sydney, or moreover, like in Australia, I would say. And it was a pleasure to me to join and to watch all of the talks. And thanks everyone for joining in person there, and for being there, and for moving to Sydney to actually deliver the talks, and for partaking in all of this. Especially thanks Danny, thanks Nico, and thanks Phil for making this possible, for making this broadcast possible without me being there. And it's not that it's important that I am there. It's just that I spent a lot of time just trying to figure out how to even make this possible, and it also took many meetings with all of the organizers, all of the local organizers there, to give them the guidelines of the things that basically had to happen, and how to do it, and the software, and everything. So thanks everyone. Special shout out to Nico, who was in charge of the blog. Round of applause to Nico. Definitely. So yeah, thank you guys very much. What I have to say, I think that in the end, it's just I'm gonna thank absolutely everyone that joined online, absolutely everyone that was a part of this since the beginning in Waterloo, throughout every single different place. It was a pleasure to be a part of this, and it has been nice to coordinate all this. The RQI Circuit is not over yet. The big hubs have presented. The big hubs, these 6 big hubs have presented so far. There will be 2 more editions of the RQI Circuit. They will be online editions. Hopefully, if you're subscribed to the IS RQI, you will get a link to join a Zoom meeting, and you'll be able to join everyone and to watch the talks being delivered from folks that are in smaller places that don't have as many people as these big hubs, and they can't really put together enough people to host like a local conference or something like this. So next Friday we're going to have another RQI Circuit. We're going to have an online edition. It's going to happen at 9 a.m. in Europe. So very, very early if you're in North America, or very late depending on your perspective. And then the week after this, we're gonna have the very last online edition. So thanks everyone for joining. Thank you guys in Sydney for organizing everything. Thanks everyone for joining. It's been a pleasure to watch everything, and I'm glad that everything turned out well. So thanks again, everyone, and hopefully I'll see you during the next broadcast. And thank you so much for organizing all of this. Danny, Phil, and Nico, you did an amazing job, and all of the presenters as well. Thank you so much.
Thank you, Rick, for organizing it. The circuits were a great idea, Rick. Thanks for organizing it.
No worries. So Nico, now feel free to hit the stop streaming button, I guess, and
all right then.
Yes, let's make an announcement. We have RQI South by Tim and Nick organized in February, and then it will be.
Where are these videos going to be posted?
They already streamed, and then it will be accessible from YouTube.
Oh, there's an RQI channel?
Yeah.
IS RQI channel, yeah.
Okay.
If you can't find it on YouTube, you can look it up on the IS RQI website. Eventually you'll find it somewhere.
Is the top as well on YouTube?
But yeah. But if you want to repeat that, the microphone wasn't on.
Yeah, let's. So if you like the show, we hope that some of you, and definitely all the people from Australia, will come up to Brisbane for the traditional RQI South this time in February. So, well, see you guys there.